Hello everyone, this is our cloud to desktop workshop. This is going to cover how to use the Google Earth Engine plugin within QGIS to get access to lots of cloud hosted datasets. The workshop will start with a bit of theoretical background for those who have not used Earth Engine before. Earth Engine has different terminology and how they organize the data. So we're going to learn a little bit more about the fundamentals of Earth Engine and the data model. Once we learn that, we're going to find different places. I'm going to show you different places where you can find Earth Engine data. And once we get comfortable with kind of where all the data sets are located, then we'll start the hands-on part where we'll do two workflows. One is we're going to pick a region and download a cloud-free composite from Sentinel-2Data for your region. And you should be able to do this without actually knowing any Earth Engine coding, just using the built-in tools that the plugin provides. And again, this is something that takes a lot of computing and a lot of time if you do it in a traditional way, but you'll be able to do this using the plugin. The next part, we're going to use the QGIS model designer to build a workflow where you can fetch data for any region using Google Earth Engine plugin, and then further process it in QGIS using the QGIS tools. And the example we're going to cover is land cover. So you're going to build a workflow where the user of your model can go anywhere in the world, select the region and run the workflow. It's going to download land cover data for that region and compute the total area of each class within that region. And again, this is something that you can build for your team, for yourself, and then the end user of your model doesn't really need to know any Earth Engine. So they can just use the model and the data will just show up in the QGIS. Just before we get started, my introduction, I come from traditional GIS and remote sensing background. I've, like somebody else mentioned, I also started my career with ArcView 3.2 and later was in the Esri ecosystem, learned MapInfo, DasImagine, and again, moved to open source once I joined Google and have been using Python and a lot of the cloud-based tools. Since then, I've worked a lot with Earth Engine. I was part of the team that taught Earth Engine for Google and worked with many researchers and scientists. And during the time, I learned kind of the pain points. And one of the things that always came up was everybody who learns about Earth Engine and say, this is really great, really powerful. Can you just build a user interface? Why can't we just click a button and get data or do some processing? And Google said it's not possible, it's too complicated. And finally, it so happens that there is a version of a user interface to Earth Engine now available that gets you access to data. So again, this will unlock many, many data sets for you. Then it's a good stepping stone into learning Earth Engine. Meghna, you can introduce yourself.
Yeah, so I have done my master's in geoinformatics and I've started automating stuff during my thesis project and then started taking interest in automating workflows, and then I explored Google Earth Engine and started developing plugins into QGIS. And I had worked with a few government and private organizations, and now as a part of Special Thoughts team, I work with Python, Google Earth Engine, QGIS, GDAL, that all the courses that we are offering.
Let's start with a brief overview of what is Earth Engine. Earth Engine is a cloud-based system that Google developed almost 10 years ago to make it easy to process satellite data. The reason they developed this was it was too hard to download and process all the data locally. So they got all the kind of commonly used Earth observation data sets, put them in live storage so you can easily access without you first downloading it or processing it. So they made it available as analysis-ready data. And they also put a lot of compute so that you can analyze the data in the cloud and only download the result. And it's been very successful. It's been operational for almost 10 years. Lots of users use this. It was started as a standalone service, and now it's become part of Google Cloud. So if you're a Google Cloud user, you can use your Google Cloud account to also use Earth Engine. And that makes it easy for people who use many different cloud services to integrate Earth Engine in the workflow. The main thing that it will be interest to a lot of you is the data catalog. Earth Engine hosts a massive amounts of data that is easily accessible. And all of this data is available by just specifying the ID or the image that you want. So you can just stream those pixels directly compared to other services where you have to download entire scenes first, and then you can have to do it one by one. So here you can kind of get ready access to 90 petabyte plus data. It's increasing every day. As soon as new data becomes available, it gets added to the catalog. So again, this is a really valuable resource for researchers, for people who want near real-time access to the dataset. Earth Engine also has a lot of computation resources and will be able to do some processing using the plugin where you can say, get me all the images for a year and give me the average value. And again, that itself requires massive amount of computation if you did it locally, but we'll be able to use the cloud resources that gets processed in real time, and you can just get the results to your computer. Earth Engine offers client APIs for both Python and JavaScript. That means you can write code in Python as well as JavaScript to access and use Earth Engine. And this is required if you want to access the full power of the platform, which can do a lot of things. But again, this is very hard for many people. You have to kind of learn the API, and it's a steep learning curve. So the plugin allows you to kind of have a gentle stepping stone into the world of Earth Engine. Earth Engine is currently freely available. So all of this data and all of this computation resources is freely available, but you need to sign up for an account. So you need to sign up for an account, you activate a cloud project, and then you are able to use this free for research or non-commercial use. It's the de facto tool now for any Earth observation research. If you read any paper that does global scale, long-term analysis, most likely they would use Earth Engine because this tool really scales quite well. There are a lot of papers that have been published using that as a platform. There are lots of people who use Earth Engine on a regular basis, and the Earth Engine team really wants to support this community. They understand it's a very valuable tool for researchers, and that's why it's freely available, and we hope that it continues to be freely available to all of you. They recently launched a commercial use tier. So if you're using Earth Engine and you're using it in a commercial setting, you need to buy a license and pay for your usage. So this is kind of new. It's been available for a couple of years now. And now if you're in a private company or you want to use the data for a government for operational use, you need to buy a subscription. And again, it's something to be aware of. You can read more about what constitutes commercial usage versus non-commercial uses on the Earth Engine website to determine if you fit for commercial or non-commercial use. So we're going to focus on the Google Earth Engine plugin for QGIS. The plugin has two parts to it. One, it adds some user interface tools. So these are the processing algorithms that gets added to your processing toolbox once you install and activate the plugin. These tools are designed to help you get data from Earth Engine without coding. So this is a no-code solution where you just say, I'm going to use these tools to add some data to QGIS, also download data to QGIS. So these are the kind of user interface that the plugin gives you to access data from Earth Engine. So that's one part of the plugin. There's another part which allows you to write Earth Engine code within QGIS. So people who are already familiar with Earth Engine and say, I know how to code in Earth Engine, you can use the code editor, the Python console in QGIS to write some Earth Engine code and see the results in QGIS. This can also be used for automation. For example, you say, I want to write a Python script that calls Earth Engine API and downloads the data programmatically. You can also do that. So again, this is for developers who want to integrate PyQGIS with Earth Engine API. In this workshop, we're going to focus on the no-code solution, where we're going to say, let's learn how to use these tools, understand how Earth Engine data is organized, so we can get the data into QGIS. The plugin has been around for a long time. So some of you might be wondering, why suddenly there is a buzz around it, and why suddenly we are offering this workshop? Well, the plugin was done by Gena, who is a very active Earth Engine user, and he said, I want to get my Earth Engine data into QGIS. And Google that time had a Python API, so he just racked the Python API and said you can now run that Python API in PyQGIS. The initial version plugin had just one thing. Once you install it, nothing changes in your QGIS interface, but when you open a Python console, you can suddenly write Earth Engine code. And when you say map.add layer, the result gets loaded into QGIS as a WMS layer. And that was useful for people who knew Earth Engine and how to code in Earth Engine to kind of get the data loaded into QGIS. But it was quite limited. It was kind of abandoned for many years. Some people were using it, but there was no real development that happened till then. Finally, Google funded this project in 2025. They said that it's important to build those tools for people to access Earth Engine data. They've been building a lot of those connectors. So people who are using other parts of Google Cloud or other GIS-like platforms, they can get access to Earth Engine data. And as part of this project of building connectors, Google funded this project to upgrade this plugin so it's easier for QGIS users to consume data from Earth Engine. Development seed was contracted to revamp the plugin. They updated the code since it was not updated in a long time, made it more maintainable. They also added this user interface, which was quite a challenge to kind of do it, and they were able to do a fairly good job to kind of build those tools to load the data from Earth Engine into QGIS. Also, for people who use QGIS, you'll see that the processing tools that you use are very different. They are dynamic. If you use any processing tool in QGIS, you select one thing and nothing else changes in real time. Everything is static. You just configure and run it. In this kind of the algorithm that they've built, you can change something and the entire processing dialog updates based on what you selected. And this is something that people wanted to do for a long time, but it's very hard. They figured out how to do this and they wrote a blog post. So if you're interested in how to build algorithms like this, do check out the blog post. And again, this is really a game changer for the developers who want to build these dynamic forms in processing algorithms. We were also funded by Google to test this plugin, find bugs, write documentation, and figure out how people might use it. And again, we spent a lot of time working with the developers, figuring out usability issues and fixing bugs and figuring out how best to kind of have this plugin be used by the users. Currently, the plugin is part of this GE community. So there are a lot of projects which are kind of initiated by the community. Some are at some point were funded by Google, but otherwise it's just a community initiative and it's an open source project owned by GE community now. There's no ongoing funding from Google. The community maintains it. So if there are bugs or features, etc., it's up to the contributors to this project to update it. So again, just for you to know the current status of the project, me and the folks from Development Seed are committed to maintaining this plugin for bugs, etc., but any kind of large features, etc., might need funding. So again, just to set expectation that you may not see a very large overhaul or some new tools in our future. But again, we'll definitely try to keep it up to date so that you can continue to use the existing functionality. The plugin is intended for two kind of users. It's intended for QGIS users who just want to get access to data. Say, hey, I see this data. I want them in QGIS. Can I get it? And that's what the kind of the sweet spot of the user who know QGIS and they want to get data from Earth Engine. Also, the QGIS users who want to build workflows will say, hey, I have this workflow where I want to build a tool for my stakeholders. They should be able to just select the region of interest, the time period, run it. You should just go and download data from the cloud wherever it exists for the region, and then I'll post processes using my model in QGIS. So if you're kind of automating those workflows, this is kind of an ideal user for this plugin. The other intended audience for this plugin is the QGIS developers. So people who write plugins, people who build stuff using Python in QGIS, that is an example. There is the plugin now allows you to write code that integrates both PyQGIS and Earth Engine API. So you can now use both of them together and do some interesting things. I've linked to this example of a blog post I wrote where you say, I want to create an animation using data from Earth Engine. Something that is hard to do in Earth Engine, but I want to use QGIS with all their print layouts and something. I can create a nice map and animate this using Python, but I'm fetching data from Earth Engine. So things like that, if you are a developer, you can also do this with plugin. Another interesting use case for developers is you want to build a plugin that relies on data from Earth Engine. This plugin kind of solves the hard part of authentication and getting everything set up. So you just say, hey, install this plugin or specify this plugin as a dependency of your QGIS plugin. And when people install and activate this plugin, your plugin can start using the tools that are provided from this plugin or even the API that the plugin offers to access data from Earth Engine. For this workshop, again, we're going to focus on the QGIS users. So let's get started with the workshop. First step is to install and set up your environment. This workshop is built on the QGIS LTR version 3.40. It should work with the latest LTR that's going to become LTR in a couple of months, the 3.44. Know that there is a QGIS version 4 coming very soon. In June of 2026, QGIS will upgrade to version 4. At that time, we'll ensure that the plugin is ready and it works with QGIS version 4. But meanwhile, make sure you use the current LTR, which will be 3.44, so that everything continues to work. This plugin requires a Google Earth Engine account, so you can go follow our instructions to sign up and obtain an Earth Engine account and activate a project. Then you'll have to install the plugin. It's going to show the plugin in QGIS. The plugin is available via the official plugin repository. The plugin is called Google Earth Engine. And once you search and install it, you should see something like this, which is the plugin that is available. Once you install it, as soon as you install it, you'll be prompted to log in to your Earth Engine account. You need to follow the instructions and sign up, log into your account. It saves a token which identifies your account on your computer so that the plugin knows who you are and what permissions you have to access Earth Engine. And you'll also have to input a cloud project, and the instructions for that are in our instructions. Once you've done this is a one-time process, and that means now every time you start QGIS, you will not be prompted to sign in. All this information that the plugin needs is already there, and you'll be continued to use this. Once you install the plugin, you get some new tools here. So you can see there is some processing tools that becomes available to you once you install and activate the plugin. If you see these tools, that means your plugin is installed and activated correctly. If you face any issues while installing or activating, there is a debugging guide that is linked from this page. So go and follow those instructions to resolve some common issues. Another note is when let's say you signed into a cloud project and you realize it was a wrong project, or maybe you said, I signed in as this user, but I want to use my other account, which is for my company. You can go to the plugin menu, and there is another sign-in option. So once you sign in, it's going to reactivate the sign-in workflow, and you can choose a different account if you wanted to. Finally, some of the exercises need some data, and there are some checkpoint projects which allow you to catch up and see the intermediate steps. So you can go and download the zip file, a fairly small data package that we'll need for the second hands-on exercise here. And once you download it, go and unzip it to a folder. Your folder should look like this. It has got one geodesy files and a solutions folder with some QGIS project. Before we dive in, what I want to do is I want to teach you a little bit about Earth Engine. And understanding where Earth Engine data lives and how to access it will allow you to configure the processing tools in the plugin much better. So we'll spend some time with some theoretical background about how Earth Engine stores data, what do they call different kind of data sets, and then we'll do a short demo of getting some data, showing how the plugin works. So just to get your brain thinking about what might be the potential use cases for you. And then we're going to try, and after the break, we're going to try and complete the first part of the hands-on things. So again, a little bit more time of just listening, understanding, and then we'll do the hands-on part. Please keep asking questions. A lot of this will be simple for existing Earth Engine users, but if you're new to Earth Engine and something doesn't make sense, please let me know. Earth Engine has lots of data stored in their catalog. The data is stored as something they called assets. So Earth Engine calls all of the data that they store as assets. There are different kinds of asset. The most basic kind is an image. So Earth Engine, if you upload an image, that becomes an image asset. So think about a single Landsat scene. That is an image asset in Earth Engine. Image can have multiple bands inside of it. So you can have 10 bands, 20 bands, 30 bands, doesn't matter. An image is any kind of image which is a georeferenced raster. So it doesn't have to be a satellite image, it can be a raster data. Any gridded pixel data can be uploaded to Earth Engine as image. It has to be georeferenced, it has to be gridded. So those are the kind of images that you can upload. If you have metadata in the image, that becomes properties. So when you're working with the plugin, sometimes you'll say, here are the properties that you need to use to filter by. Properties are the metadata. By default, when you upload some GeoTIFF files, GeoTIFF file doesn't really have a standardized way of having metadata. So Earth Engine users, when they upload data, they typically specify it by hand. If there is a metadata that comes in a different file, it can be encoded into the image as properties. So if you see an image in Earth Engine, likely they'll have some properties, which is the metadata about the image. It'll be things like image ID, image collection date, any other kind of information that what satellite captured it, and so on. So those will be those are called properties. One unique thing about Earth Engine images compared to, let's say, GeoTIFF files is each band can have different data type and different projections and different resolution. This is something that is not supported by most data formats that you use in your GIS software. If you use GeoTIFF files or any other files, they expect that if you have 3 bands, they are the same type, they are the same resolution, they are the same projection. Earth Engine has a more flexible data model. So if you see an image, they might have like 3 bands. One might be a binary band, one might be a floating point, one might be an integer band. Each of them might be in different projection, and that's totally fine. Earth Engine supports that. Something to be aware of if you're working with multi-band images, you might have images, a band, which are in different projections. The next bit of asset that Earth Engine uses, which is the most commonly used asset type in Earth Engine, is called an image collection. As the name specifies, it's a collection of multiple images. So let's say you have images, you upload 10 images, and then you put them together into a collection. So an image collection can have multiple images, both over space and time. That means if you have tiles, lot of data set so large that they will provide you as tiles. So let's say you have 100 tiles that cover the whole country. If you upload all of them, they can all be part of the same image collection. You can also have images over time. That means if your satellite is getting the data every week and you have data for a year, you can just store all of those yearly images in a single collection. Most data sets that you'll find in Earth Engine are image collections. There are a few which are just images, but most of them will be image collections. And image collections are more flexible and you can do a lot of interesting things. So even people have a single image, they would actually upload them as image collection. And that just is a little more flexible data container for that. So when you're looking for data, most of the time when you go and find some data, you'll see it'll be image collection. And that means you need to use the right tools and algorithms that can work with this data. Lastly, there is a data type called feature collections. Feature collections is vector data set. So shapefiles, if you think about shapes and attributes, those are stored as feature collections. So let's say you have data of all the roads in a country. That's a feature collection. Each feature is a road with some metadata, which is your attributes. So geometry and attributes are stored as features, and they are stored together in the feature collection. Feature collections are also quite common. They're available. We're not going to focus on vector dataset for this course because there is no really easy way to download this data to QGIS. Most of the stuff that we're going to focus will be on image collections and images. There are multiple ways you can get access to the Earth Engine dataset. The main place where you should look for data is the official Earth Engine data catalog. Again, lots of data sets. There are 1,000+ data sets available. Each dataset is things like Sentinel-2 is one dataset, which has got millions of images, and it's petabytes in size, right? So there are 1,000+ individual datasets that are available. Each dataset may have different images or feature collections inside of that. So again, very, very large repository of data. These are continuously updating. So things that the active satellites that are collecting data, as soon as a new image is available, Earth Engine fetches it and updates the collection. That means if you are looking for some data from yesterday, it should be there in Earth Engine already. You don't have to go and update your code or update your workflow. So if your workflow says, get me the latest data from Earth Engine, your workflow will continue to work even 6 months from now as the collections keep updating for that. So it'll be great for getting near real-time data. And they do all of the data that gets ingested into Earth Engine is analysis-ready data. So they are harmonized for projections, pixel size, all of those corrections that need to be done are already done. So you should be able to get this and start using this right away. Let's give you a tour of the official data catalog, and then we'll go through other data sets. I'm going to click this link. This is the Earth Engine data catalog. You will come here to this link. You can just search for Earth Engine data catalog and you'll end up in this page. This page is organized at the top by the 3 main data sets of Earth observation. So if you're looking for some Landsat data or MODIS data or Sentinel data, you will come here and find it. So for example, let's say I'm looking for some Sentinel data. You'll come here, and these are the different Sentinel data sets available. This is Sentinel-1, Sentinel-2, Sentinel-3, 5P, some derived data sets that are available from Sentinel-2. All of those are available here. Let's say I want to work with Sentinel-2 data. I would come here, and again, there are different versions of this data set. Let's say I want to work with this data set, and you come here, you can read a little bit more about the data set. So again, it's important to understand how the data set is organized so you can kind of make use of it. What's the time range? You can see the time period that's available. The most important for the plugin users is this ID. And you can see this one is an image collection. So you come to this page of any data set and you say, oh, this is actually an image collection. So I'll use the appropriate tool for that. You will also see the bands tab, which will list all the different bands. that are available in the dataset and the resolution. As I mentioned, Earth Engine images can have bands of different resolutions. So you can see this one is 60-meter data, this one is 10-meter data. There's some description that is available. You also have image properties. So this is the metadata that is available with each individual images in the collection. So you can say, I have one image, what's the cloud percentage? And that is available in this property. Right, so all the metadata is described here, all the bands are available here, the resolution is described here. In Earth Engine, when you are looking for resolution, it's always in meters. So even if your data set might originally have been in lat long, you still always use the resolution in meters. So just remember to just check this page to see the resolution. If you want to search, you can also search for a specific data set. Let's say I'm looking for some elevation data. I want to download the data from SRTM. Have this data set link. And you can see there's the data set that's available here. The first thing you notice, this one comes in as an image. It's not an image collection. Right? So if I want to load this data, I would just go and use this ID, but it's an image. It's not an image collection. And there's some description. There's got only one band. And again, the units are given here. The size will always be given in meters. So you can use that. And there are some metadata that there's no metadata with this. Another thing to kind of learn is the terms of use. Almost all the data sets that are in the catalog are free and open. That means it's completely free to use. It's openly licensed. Some may have requirements such as you should cite the use of the data. There might be some data sets which will say, oh, you are restricted in using this data in certain settings. Or you need to kind of fill this form and get access to data, things like that. So make sure you read the terms of use, which will describe the license of the data. And then if there's a citation requirement, there's a citation. So that when you use the data, make sure you cite this in your paper so that the data author gets the credit for that. There may be other polygons for example, I want to get some data for oil and gas. There is this really amazing data set called OGIM, which is mapped all the gas pipelines, all the wells of the world. And you can see now this one is a feature collection. So this is a vector data set in Earth Engine. The vector data set page will look different. That doesn't have bands. It will have attribute table, right? So this is the table that each of them have. So again, each point, line, or polygon will have a category and some IDs, etc. And you can use this. So again, you can read more about the data set. Similar to image collection, this is a very flexible. So a single image collection can have some points, lines, polygons, everything together. It's unlike shapefiles where you just have to store one data type in a single shapefile. So we learned about 3 different kinds of data sets that are available in the catalog. You have image collections, images, and feature collections. And you can use this catalog to either search or even browse for the data set. If you're looking for some data and say, I just want to know what climate data set are there, I can just go and click on this climate category and go and kind of browse all the data set that is available here. And all of those data that you see here, you would be able to access this using the plugin. Let's do a quick demo of getting some data from this catalog. There's a new data set that was released recently. Deforestation is a big theme for people studying environment and climate change. And there are many, many great global forest data sets. Forests are also important for regulation. There is a regulation in Europe called EUDR, which says if you're supplying certain commodities to Europe, you need to prove that they were not grown in a farm that caused deforestation. And many people are interested in saying, hey, I'm buying my cocoa from this farmer. Do I know that this was a forest land before? And the deadline for this baseline year for UTR is 2020. That's why you see a lot of this data sets are 2020 baseline data sets. And these are primarily used to track deforestation for regulation purposes. There was this new data set that was recently released, which has mapped forest with higher accuracy. They also have differentiation between natural forests. So again, if you're interested in natural forests, this is a great data set. You can see certain limitations and certain caveats about this data set. But again, this is a very high quality data set about map of forest as it existed in 2020. You can see this is a 10-meter resolution data. So you have 10-meter pixels everywhere in the world, which says, is this a forest or not forest? There's a band called base 0, which has value from 0 to 250. It is a probability. So again, you can think of it as a percentage. So it's 100%. Forest model is very confident that this was a natural forest. The value will be 250. The model says, I'm not very confident. The value might be between 0 and 250, right? So this is like a scale value of percentage probability of it being a forest. Now, is it I learned about this dataset. I want to use this in QGIS. Let's do a quick demo to see how we can load this data. At this point, do not do this yourself. We're going to do step by step together. Just understand how this thing works, how to find data, where the ID is located, how the tools work, just to kind of open your minds to how the plugin work, and then think about what data set you might want to use for that. Let's load some base layer. I'm just going to go and load some OSM base layer, and this gives me a nice base map. Let's say I'm interested in tracking forest around Western Ghats in India. This is a very ecologically sensitive region, and I want to know what parts were forest. So I want to get data for that. So I can zoom into a region and say, let's say I want to understand forest cover in this region. Imagine how would you do this before? You would go to this some website, they'll give you maybe a 10 GB download of a GeoTIFF file, or maybe they give you tiles and you have to download each of this. Here, you just say, hey, I have this plugin, I want to add an image collection. First thing it's going to ask you, what's the ID? So I'm going to go and say, copy my ID from here. And as soon as you put the ID, you'll see the plugin slightly refreshes. So that means it's going to go and query Earth Engine to say, does this ID exist? If it exists, what are the different bands and properties that are available to me in this? So here you can see the band is B0 is available now. So this was fetched dynamically. If you do not see any bands here, that means your ID is wrong. So sometimes even when I copy paste it, I may have forgotten one character, or I might add an extra space, and then it doesn't work. So make sure once you do this, the plugin will slightly refresh, and then make sure you have some bands available to you. We'll say I want to get data from load data for this map extent that I have. I have this one band, and I want to visualize this with green colors, and I'm going to visualize from 0 to 250. So as we learned in the data catalog, that the values range from 0 to 250. 0 will be white, 250 will be green in this case. We have this option clip to extent. So if you do this, the layer that you'll get will only be available for this extent. If you uncheck it, it'll be available globally. You can zoom and pan anywhere for this. Let's run this. When I run the plugin, what's happening right now is it's sending the request to Earth Engine servers. The Earth Engine server says, hey, the user wants to visualize this data in this particular way. Earth Engine sets up a temporary WMS service. So it sets up a special WMS service that is meant only for you for visualizing this data. A layer gets added to QGIS that is connected to that WMS service, which is just set up temporarily for you based on the configuration you did. So the data comes in as a tiled layer. So if you think about or XYZ tiles or kind of base map tiles, this is what you'll get. As soon as you can load the layer, you see there's nothing appearing because the canvas needs to refresh a bit for it to trigger the fetching of the tiles from the temporary WMS service. So you can just use the pan tool to move the map slightly, and you'll see now that the tiles are being fetched now. And you can see I have a map of forest that I got from this data set that was fetched live from the server. I didn't have to do any coding. I just have to go and find this data. I can also inspect the pixel value. So if I use the identify tool in QGIS and click on a pixel, the identify tool is also wrapped using the API. So it's going to go and ask Earth Engine, what's the pixel value here? And it says this value is 237. Right? So I can also identify the value that is loaded. There are tools. So we're going to use this tool later in the workshop to download this as a GeoTIFF file. So this is for visualization only. If you want to create a map, you can now go and just create a print layout and create a map without even downloading it. But this acts just like any other tile layer that you have in QGIS. But if you want to get access to the raw data to do some analysis, you can go and add the export to GeoTIFF. Great, so I have my forest map. I can kind of see that all the pixels were forest in 2020, and I can have that information here. Let's load some other data sets. So what are other ways you can get data sets from Earth Engine? There is another great place to get data from Earth Engine. That place is the Earth Engine Community Catalog. This came about when a lot of researchers were creating data sets and saying, hey, I did this research. I made some deep learning model that created this data set. And they would publish it somewhere, but it's hard to find. Typically, they would be linked from their paper, or it would be in some Zenodo repository, but it's very hard to discover. So this data set is not easily discoverable. Plus, even if you found the data, let's say you got a download, typically many global data sets will be, say, 500 GB download and in some many tiles. even uploading them to Earth Engine will be a mammoth task. So this catalog started as a way to expose all this amazing data set that exists and also get them into Earth Engine so that you don't have to download it yourself. You can just say point to this ID and you can start using this. This project is led by Sampri Roy, an amazing contributor to Earth Engine, and he's put a lot of effort and he's kind of single-handedly maintains this with some help from community members. Let's go and browse the community catalog and load some data from there. The community catalog is a treasure trove of data set. You'll have amazing data set that you never know existed. If you are embarking on a new project, I highly recommend you come and browse the data set here. Not only for Earth Engine users, for non-Earth Engine users as well, all of this data set are linked with the source data. So you say, I don't even want to do anything with Earth Engine, still you'll find the data and the source data that you can download for use in your projects. The data catalog is organized by different themes. So you can go and browse some themes. For example, if you want to get some utilities data, there are a bunch of data for utilities. There's a new data set that just came up, Global Building Atlas. This is all the 2.5D buildings of the world, millions of polygons of the buildings. And again, it's already in Earth Engine data catalog. You come here, you'll see the citation. So you can cite the paper if you want to use this. If you just say, this is great data set, I want to use it in my project, but I don't want to use Earth Engine. Maybe I'm a commercial user, I don't want to use it, or I don't know Earth Engine. You can go and browse the data set, the original data set from here, and you can download it. So you can use it there. So again, for data discoverability, it's a great thing. Similar to the main catalog, there is some code available. There's some description on how the data set was processed. So you can browse and look at this data set. You'll also see the ID here. So you can see this one is the feature collection. So again, they are polygons. So they are served as a vector data. There are many, many data sets. Maybe you are interested in deforestation and mapping trees. You may be interested in this data set from Facebook, where they mapped tree canopy cover at 1 meter resolution globally. So this was the data set that was produced by the team at Facebook, where they used high resolution imagery and predicted the height of trees at every pixel at 1 meter resolution in the world. An amazing data set. At every 1 meter, you know what's the height of the tree. If you were to get this data, again, very, very large data set, and to download it and process it. But it's now uploaded in the community catalog, so we can start using this. And you can see this one is an image collection here. So I can just start using this data. They also will provide some code. The code is sometimes useful to say, hey, I'm trying to visualize this data. What's the right value for my min and max? So the example code will give you some hint at what min max value should use. So here, let's use this ID here. So this is the canopy height data set. This one is from the community catalog. Again, once you do the ID, it should be able to show you some band. And you can see there's a band that became available. So there's only one band in this data. We'll also say, I just want to get data for this region. And here, let's visualize this in maybe this color ramp and the min max value. So this is the height of trees at every pixel. And if you see the code, they recommend 0 to 25 meters. So that means the tree of 0 height will be in black. The tree of 25 and above will be in this bright yellow, and every in between will be in this different color. Okay. Let's run this. It's sending the request to Earth Engine servers saying that, hey, you have a data set, I want to visualize like this, set up a WMS service that I can connect with QGIS. And now once it loads, I just move my map slightly and start fetching this data from the server. And you'll see that this is the tree height data that is now loaded into my QGIS. And you can see it's a pretty high resolution data set that I was able to use this and load this in Earth Engine. Similar to before, I can also inspect it and say, hey, what's the tree height at this pixel? And I'm going to query the server and say, this is a 15-meter height predicted at that. So now I have two data sets. I have the map of forests. So I have the map of forest and I have the height of trees. want to show you the third way. What's the other third way you can access this data? So we saw that we can go and find data set from the main catalog or the community catalog. What's the other way that you can use Earth Engine data? Well, any user of Earth Engine can upload any data to Earth Engine. And once you upload it, you will have an ID that can be used and loaded into Earth Engine. If you are an Earth Engine user and you say, I have run some ML model and created this new data set, it's available in my account as an asset, I can just load it into Earth Engine. If I have an asset I've shared with my team, all of your team members can use this ID in the plugin and they can load this. If I have an image which I've made it public, anybody who has the ID can use it. So again, your colleagues, yourself, your team members can use dataset that they have uploaded into Earth Engine. We had looked at this dataset from the community catalog. If I open this code example, you can see this code example compares this Facebook's data with other projects and other users' data who have also mapped tree canopy height. So say I really want to get access to some other data and compare them and see which one works best. You can see here, there is somebody from ETH, this user of Earth Engine, has created a canopy height dataset. And it's available here. And it's a public dataset, so I can just copy this and say, hey, here's an image that I want to load and compare it with the Facebook layer. So again, this ID, I can use it. You can also see this is an image. So I want to load this, so I need to use the tool that will allow me to load image. So far we've been using image collections. This is image, so I can use this image. Similar thing, load the data, map canvas extend. This one has a one band called B1. Let's load it in a slightly different palette, the same visualization. So again, this goes from 0 to 25. And now I run it. I get this image, which was created by the user, available in Earth Engine, and now I can stream it into my QGIS. One point to note is every time you move the map, it sends a request from all those 3 layers that are enabled in your QGIS to update it. And that can get quite cumbersome. So what I like to do is when I don't want to use any data set, I will just turn it off so that doesn't get refreshed when I move the map. So make sure you turn off any Earth Engine layers that you don't use. That will really improve your user experience as you're moving in QGIS. So now we have loaded this new dataset that we found uploaded by some user. And now as I move the map, it's going to go and fetch those tiles. And you can see this is again a tree canopy height map that is produced by somebody else and it's now available to you. Ready to do our hands-on part where we'll actually work with the plugin step by step and load some data. These are the 2 workflows that we're going to completely do step by step. The first one is downloading images from Earth Engine. So let's start that. This workflow is documented step by step on your course material here. So in case you want to follow this as a text step by step later on, you can use this. Right now, we're going to do this. I'm going to do each step on my screen. We'll give you time so you can follow and replicate it. And then we'll have completed the whole workflow for downloading images. Let's open QGIS. I'm using the QGIS version 3.40, but any recent version of QGIS should be fine. At this point, I have installed and activated the Earth Engine plugin. I see the processing tools here in my toolbox, so we are ready to go. For this workflow, what we're going to do is we're going to pick a region anywhere on Earth. You can pick any region of interest, and we're going to download a cloud-free median composite from Sentinel Imagery for your chosen year. And we're going to download that as a GeoTIFF file. So we're going to go through and see how to do this. So first, when you start QGIS, you get this blank canvas. You really don't know where you are. It'll be nice to get a base map loaded into QGIS. QGIS comes with a pre-configured base map. So if you go to your QGIS browser and scroll on the left side, you'll see the section called XYZ tiles. And if you expand it, you should see at least one. Maybe there is also MapZen available to you. So OpenStreetMap, this comes pre-configured with your QGIS. This allows you to load pre-rendered OpenStreetMap tiles into QGIS. And this is a great way to get some base map into your QGIS. I'm going to go and drag the OpenStreetMap layer here. And this gives me a world map, which I can use to go and locate a place. You can see I have many other. If you have a URL of a tile server, which has got tiles, XYZ tiles, you can right click here and add a new connection. Now we're going to go and find some place. So let's say I zoom in, pan some region which I'm interested in, and I'm going to get some satellite data. Maybe I'm interested in New York and get some data. you can browse and pan to that place. But we're going to also use a nice feature in QGIS to search for a place. Modern versions of QGIS comes built in with a geocoder, so you can type a place name and zoom to that place. The geocoder can be accessed from the bottom left corner of QGIS, where there's a search button and says type to locate. If I click here, it brings up this help. So there are many things you can search using this toolbar. If you have a vector dataset loaded, you can actually search through attributes and find the feature. You can search for layer and a bunch of other things. You can search for an algorithm and launch that. So it's a nice search box, like a universal search box. The third one says nominatim geocoder. So you start with this greater than sign. So to trigger the geocoder, you use the greater than symbol and add a space. And now you can type any place in the world and will show the matches from the nominative geocoder. This is based on OpenStreetMap. Let's say I want to go to Paris. So if I search for Paris, it's going to show me all the matches, and I can just double click the first one, and now I am in Paris. Okay, so you can use any place name that you're interested in, and you can just fly to there. Make sure that when you type this, you type greater than, add a space here, and then type the place name. The geocoder is based on OpenStreetMap, so you need to kind of spell it the way OpenStreetMap spells it. Sometimes you have a city which have multiple cities in the different countries. It helps to say, I'm looking for, say, Paris in France. So again, you can specify what country you're looking for, so you can use that as well. So we have now found a place. What we want to do is for this region, I want to download Sentinel-2 imagery. And not just one image, I want to create a composite image, which is the average observation from tens or many more Sentinel-2 images, which are collected through the year. And I want to get the average value. And average value is useful because Sentinel-2 imagery is an optical sensor. You'll have clouds and cloud shadows. So if you just say, give me one image, it might be cloudy. If you just want to get a representative pixel, you can choose the time period and get a median value, which will likely be a cloud-free pixel. And this is a common type of analysis that you need to do when you're working with Earth observation data. You can directly get this from Earth Engine. You are able to load and download very large data set from this plugin. But if you're downloading very large region, it might take a while. It might take like 30 minutes to download it. For the purpose of the workshop, go and zoom in slightly more. So we pick a smaller region just to test the workflow. We don't want to spend 30 minutes waiting for a download to finish. So a small suburb of a city is a good region to try this out. If you are in a big city, maybe zoom into a smaller part. If your city is small enough, you can keep it like that. And you can adjust this later on. When we start downloading, it's going to tell you if your region is too large, it's going to give you a warning saying there is this very large region. Maybe zoom in a little bit more so we can download this in a reasonable amount of time. Okay, so here is my data that I want to download. Let's go and tool. So you have the plugin here. There's an add layer section. We want to add the Sentinel-2 image collection. So we're going to use this tool. So from your processing toolbox, if you don't have the toolbox open, you can open it from processing menu, open the toolbox. At the bottom, once your plugin is activated, you should see these tools. Go and find the add image collection tool and double click it. This will bring up this dialog, which we will have to configure to specify what image collection we want to load and with what visualization. The first step, we need to find the ID of the dataset that we want to launch. So we'll switch back to our Earth Engine data catalog. So from the data catalog, we're going to go and find the Sentinel-2 dataset. This is easily accessible from the top menu here. You're going to go and pick Sentinel-2, which is a nice medium resolution dataset, optical dataset, very widely used. It's completely open and free, and it's got high temporal frequency. You get a new image everywhere on Earth every 5 days at fairly high resolution. And this is widely used for Earth observation data. You can see here there are two versions. Satellite captures an image. That image is level 0. That's a raw data. You can't really use it in your GIS environment. At the minimum, you need to have it processed to level 1, which is georeferenced, orthorectified, and corrected for all the different effects of sun, geometry, and seasons, etc. So once it's corrected, georeferenced, and you have a reflectance value, that's a level 1 data. So this is the level 1 data. This one still has the effect of atmosphere. So the light has passed from the ground all the way through the atmosphere and reached the satellite. And that means if your atmosphere had different content on 2 different days, you will get different reflectances. And that's not right. You want to make sure that the same object will have the same reflectance regardless of the atmosphere. So you have a model of the atmosphere, use some data set, model the atmosphere and correct for the effect, and you get the level 2 data. So level 2 is kind of the more processed and correct version of this data. So whenever there is level 2 data available for satellite data, you should use that. Earth Engine has level 2 data for Landsat, MODIS, Sentinel-2 all readily available. You don't have to do atmospheric correction yourself. So let's use this data set. This is an image collection. So we have our ID here. And you can see this one is a full time series. You have images available from 2017 all the way till yesterday. So you can go and copy this ID. When you copy the ID, just copy the text. Don't copy the codes or the image collection. So I'm going to copy this and paste it in my QGIS algorithm. If everything went well, you should now be able to go and see a list of bands here. If you see a list of bands, that means the ID was correct. You didn't make a mistake and it found and loaded all the bands that are available. So this is a good check to do before we configure anything else, that when you pasted this, make sure it'll refresh the dialog slightly and load all the available bands here. Now this image collection has many images. It has got all images that the satellite has captured since 2017 everywhere on Earth. And that means there are millions of images. It's petabytes in size. Most likely, you don't want all images ever collected by the satellite for your project, right? You need data for a specific time period, for a specific region, with a specific matching certain attributes. So the next step, you can see there are different sections here where we configure what images do we exactly need for our analysis. And those are called filters in Earth Engine. So we apply a bunch of filters and say, hey, I don't want all of those millions of images. Filter it down to the images that I specify. So let's learn about some of the filters that are available here. We'll dive back into the presentation here. A little bit more theory about filters and how do they work with Earth Engine. When you're working with image collections, you have to filter it down to the images you need, and then you can finally load the data. In the Earth Engine API, there are hundreds of filters. You can do many advanced things. It's not possible to build a user interface for all of those hundreds of filters. So the plugin exposes 3 main filters that you can use for selecting the data you need. The first one is a date filter. You can specify a date range. So you can say start and end date, and whatever images are collected between those dates will be selected. So, and the dates can be specified in the ISO format. You can just say year, month, day. So if you want images from yesterday, you'll say 16 December 2025 to 17 December 2025. Right? So that's a date range. You can say, I want images for 1 month. You can specify first, say, I want all images of January. You specify 1st Jan. And the end date in Earth Engine filters are excluded. So if you say my start date is 1st Jan, end date is 31st Jan, the images on 31st Jan won't be selected. So the end date is exclusive. That means you always add an extra day in your date filters. So you say my start date is 1st Jan, end date is 1st Feb, if you want all images of January. This is super important if you're especially working with climate data. This can cause wrong results because you're excluding certain days that you are supposed to include in that month or a week, etc. So make sure you understand that the end date is exclusive in Earth Engine API. Okay, so that's a date filter. You'll select the images that you need between the 2 dates. Second is an extent filter. Do we want all images everywhere in the world? No, we just want images that is in the region that I specify. All other filters in the plugin are optional. The extent filter is required because it's generally not a good idea to load global layers. So it forces you to specify at least some extent. It can be a very large extent, but you still have to specify an extent so that you are able to select images that match that. If you have some metadata, you can say select images that have certain properties. So you say, oh, this image has certain cloud cover. I want images which have less than certain cloud cover. So you can go and select that. Okay, so these are the three main filters that we'll use. Let's go back to QGIS and configure our tool. So the first option here is filter by image properties. So I'm going to expand that, and you'll notice that this is already pre-filled with all the properties that are part of this image collection. So you can just pick the property that you want. Here, what we want to do is we want to select all images which have less than 30% cloud cover. What property holds that? Like, I have no information here. So I want to go back to my Earth Engine data catalog and say, I go to image properties, and it has got description of what each of those values mean. Here we're going to use this property, cloudy pixel percentage. It says, what is the total cloud percentage in the whole image? So if the image is very cloudy, it might have 90% cloud cover. If the image has no cloud, it will have 0 value. So we can say, I want to select images where this value is less than 30. So you're going to remove very cloudy scenes from your analysis. We can specify it here. We'll select cloudy pixel percentage. You can also type C and to jump through that. But there's a property called cloudy pixel percentage. Here, from equal to, we're going to change it to less than and say 30. This filter will ensure that the images that you get have this property, cloudy pixel percentage, less than 30. Make sure when you configure, you change this to less than. If your results come back empty, the main reason will be you might have it equal to. It's unlikely there are images which are exactly 30% cloud cover. So you need to make sure you say less than 30%. And there's no percentage sign. Just say cloudy pixel percentage less than 30. Next section is compositing. I'm going to explain this in a bit. Keep that. Let's add one more filter on the date. So I'm going to open up this filter by date section. And what we want to do is, for the selected region, we want to select all images collected during one of the years. So an entire year, whatever images the satellite is captured, we're going to select all of those images. Let's select 2024. So I'm going to add here, there is a nice calendar widget you can use, but it's easiest just to type in the values. So I can just select the first value, type 010124. So this is the 1st Jan 2024. So you can just go and select the first value and just type it in. Just the fastest way to kind of type it in. The end date, we're going to select all images collected in 2024. So the end date will be 010125. Remember, Earth Engine date filters need an extra day. If you enter 31st December 2024, if there was images collected on that day, it won't be selected. So make sure you add the end date as 010125. This widget is a bit finicky, so if you don't get a hang of it, it's okay. Try a couple of times. What I find is easiest is just double click on the first bit and then just type it in. That just makes it quite easy to type in the values. The next one, going to open the bounds filter. This is what's the extent which you want to select images from. For most of the time, it's just easiest to click this button, map canvas extent, and this will fetch the extent of the viewport that you have on your map, and that will be selected. Sometimes though, let's say you have a shapefile that is loaded in QGIS, and you say, I want to match the extent of the shapefile. You can also say select from some layer. So if there's a layer loaded, you can just select this layer and it'll be extent of the layer that you can use. But for now, just click map canvas extent. It's going to autofill these values, and we'll get images that intersect that particular bounding box. Done. So far, we applied 3 filters. We applied a date filter to select images less than 30% cloud cover. We applied a date filter to select images collecting 2024. And then we applied this extend filter where we say select images that intersect this region that I have zoomed in on my QGIS canvas. There's one section here called compositing, and you have multiple options here. Let's understand a little bit what of these options mean. I'm going to switch back to slides. When you work with image collections, you typically end up with one or more images after a filter is applied. So let's say in your region for 1 year, there might be 30 images that are collected, which are less than 30% cloud cover. Now, what should be your final image? How do you create your final image from all those 30 different individual scenes? One option is mosaic. Mosaic means you stack the images by date, and whatever comes on top, that will be the image. This is useful when your image collection is tiled. There are many image collections which have different tiles for different regions. So you say, select all the tiles for my region and then mosaic them. So that'll just merge them and select the topmost pixel. So if your data is distributed spatially, which you want to just get as a single image, mosaic is the one. Mosaic is also a good default. In case your image collection has only one image, it'll be that image. So many times you say, I have my image collection. After applying filters, it just ended up with one image. Mosaic will just give you that image. So mosaic is a kind of a good default to have that will just give you either the last image in your collection. If you have 30 images, mosaic will give you the last image. Or if it's spatially distributed, it'll give you the combination of all the images that are in your region. There's a median one. Median is especially useful for optical data or data which has outliers. Median is more robust against outliers. So if you have cloudy pixels, which will have very high reflectance, cloud shadows, which have very low reflectance, a mean value will get affected by those outliers. So median is more suitable for Earth observation data. You say, I have applied my filters. I end up with 30 images in a year. I want to get the average value. Median is a good compositing method to select. So go take each pixel, get all the observations, and then give it the median value. And this is useful to create like a cloud-free composite that you have. Mean is just average. So this is useful for like climate data or any other raster data, which doesn't have outliers. So if you say I have 10 images of temperatures collected during this period, I just want average value at each pixel. That's a good average. There's also one thing called first. This is useful because there are many data sets where there's only one global image, but it is still given to you as an image collection. You say, oh, I know that there's only one image in the collection. So you just say, give me first. And they just give you their first image out of that. So these are the kind of different compositing methods. Again, if you are an Earth Engine user, there are hundreds of compositing methods. Only these ones are exposed in your tool, which are most commonly used. Okay, let's go back to our QGIS. We're going to open the compositing one. We're going to now switch to median, where we're going to take the median value of all the images that are collected during this year. At this point, you should have a property filter applied, median compositing method selected, applied a date filter for these two dates, selected the map canvas extent, and finally, we want to visualize this data. How to visualize this data? Now, if you see this dropdown, there are many bands. If you want to know what each of these bands mean, again, these are all documented in the catalog where you found the data. So let's go back to the catalog, switch to the bands tab, and then here we have the description of the bands. We can only select 3 bands at most to visualize the data because computers and human eyes, we can only see 3 channels of information at once. So whatever 3 bands we select, they'll be composited into an RGB image, and that's what we'll see on the screen. We can create a natural color composite where we'll say, let's put the red band in the red channel, green band in the green channel, blue band in the blue channel. And they'll give you an image which is natural color. So if you are flying over the region, this is what you will see. You can also select other bands and create false color composite if that's what you wish. Feel free to try this if you want. So I'm going to select band 4, 3, and 2 as my bands. And all of these bands, if you read the documentation, they have values from 0 to 10,000. 0 is 0 reflectance, 10,000 is reflectance of 100%. most of the values of these bands are between 0 to 3000 because most materials on Earth have a reflectance of 0 to 0.3. So whatever band you select, most of the values will lie between those two. So a good min-max value to use for visualization is 0 to 3000. You can also change it to get either low contrast or higher contrast visualization out of this. And again, the visualization parameters do not change the data value. They'll only change how the data is visualized. And when we inspect, we'll actually see the pixel values that are there in the original pixels. Let's configure our visualization parameters. We'll do B4, 3, and 2. This is the red band in the red channel, green band in green channel, blue band in blue channel. When we have 3 bands, we don't specify a color ramp. Color ramp is only for single band images. When we have single band images, we say display the values from this color to this color. The 3 band images will be composited based on the pixel value by the combination of the values in those channels. So we don't specify the color ramp. We'll select 0 to 3000 as the min-max value. And for now, keep this clip to extent on. That means only the data for this viewport that we have used will be loaded as the WMS layer. Once you configure this, go and click run. It's going to take a few seconds and a new layer will be loaded into your QGIS canvas. Once again, a review of the stuff we have done. We added the image collection ID, applied metadata filter, selected median as a compositing method, applied a date filter for 2024, applied the extent filter for the current map canvas extent. We have 4, 3, and 2 as the band selected, no color ramp, and we selected 0 to 3000 as our min-max values. I'm going to click run. And this request will go via the Earth Engine API to the Earth Engine servers. It's going to now set up a temporary WMS service that will serve the tiles in the visualization that you requested for the images that you selected using the filter. And you should see a new image loaded in your layers panel. And when you load by default, you don't see any data. You need to pan your map slightly or change the extent a bit, and then you'll be able to see those tiles. And you can see these tiles are being served live from the Earth Engine servers as WMS tiles. And you can see this really nice, beautiful cloud-free composite that was created on the Earth Engine servers and streamed to your QGIS. If you had to do this, imagine you had to download 30 images of 5 GB each to your computer, spend maybe a few hours of computation to do the median value, and then you'll have this. Now you have just fetched this live from Earth Engine. There's also, the tiles are served live at the resolution that you are looking at. So for example, if I use the zoom tool and zoom to a region here, you will see that a new tiles will be fetched where it'll say, now I'm at the scale of 1:28,000. Create the median composite from all the images at that resolution and serve me those tiles into QGIS. And you can see there's a progress bar here that is kind of fetching the tiles. Once those tiles are fetched, you'll get those streamed in to QGIS and you'll see a more sharper image visible on the screen. Now we have this data, it looks nice. Maybe you can use it to create a map if you need to do this. But for most of you, you want to take this as download it to your computer and save it as a GeoTIFF file so you can analyze it further. Maybe you want to compute NDVI, you want to take ratio of 2 bands, or you want to extract some features. All of this can be done only on the actual pixel data. Here you don't have pixel data, you just have tiles. So the plugin provides you with an export tool. So let's open up the export tool. The tool is called Export Image to GeoTIFF. This tool will allow you to select an image and configure how you want to download it. If you have multiple images loaded, it'll show you in this drop down here. Only the images which are currently enabled will be shown here. So if you turned off the layer, it won't appear here. Make sure the layer is enabled and you can select the image. Let's configure this one. It's going to ask you what resolution you want the output GeoTIFF file. Here, whatever resolution you select, all the bands of the image will be resampled to that resolution and downloaded. So if you have 2 bands of different resolution you want to download, you have to choose one of the resolutions. If the resolution is higher, the image will be upsampled. If the resolution is lower, the image will be downsampled to that resolution. Let's do 10 meter because most of the bands are 10 meter resolution and we want to keep the full fidelity of the data. In Earth Engine, scale is always in meters. So just remember, if you don't know what's the equivalent value in meters, that the catalog will always list the size of pixel in meters. That's what you'd use here. Projection. We need to select an output projection that will have a GeoTIFF file. And again, this is useful because you can now automatically get GeoTIFF file into the projection you want, not the source projection. Earth Engine will reproject and give you an image in your desired projection. If you know a good projection for your region of interest, you can go and select it from this selector here. This is a CRS selector. You can go and find the projection that works for your region. If you don't have a good projection and you just want to have a projection that works decently globally, you can use the code 3857, which is the pseudo Mercator projection that Google Maps uses. So it'll appear the same as it appears in Earth Engine code editor or in Google Maps. So this will be the same projection that your image will be reprojected. So if you don't know a suitable projection for a region, use this for your region, which is okay. Ideally, you would want something that is more accurate for your region. UTM is a good choice. So if you know the UTM projection for your region, you can go and find that here. I know that the region that we are working with, Paris, is in the UTM projection of zone 31 north. So if you know the UTM zone of your region, you can just search. So this is UTM zone 31 north. And you can see I found this projection, which is based on WGS84 datum, UTM projection in zone 31. It's also a nice red highlight. It says this is the region where this projection is valid. And I have the projection selected here. If you want to find the UTM zone for your region, this is an interactive map where you can just search for a region. So let's say we are looking at Paris, search for the region. And when you click on this, it'll show you that you are in UTM zone north. So again, you can feel free to use this tool if you wanted to and get the zone number of your UTM. If you don't want to do this, just use 3857 pseudo Mercator, which is a decent projection to use for most parts of the world. I'm going to select the EPSG 32631 for Paris. If you're in the selector, again, don't click run. This one, once you select the projection, you need to click this back button to go back to your configuration. Once you have projection, it says what extent you want to download. And right now I'll just say map canvas extent. So this is the extent that will get downloaded. You can also select what bands you want. Even though we visualized only 3 bands, you can actually download multiple bands if you want, or just a single band. So download is separate from visualization. Let's select band 4, 3, and 2. You can hold the shift key and select multiple bands, put them on the right side. You can also change the order because the GeoTIFF file will have band 1, 2, 3. You can select which order they appear. You can also change the order if you want. You can also remove certain bands if you select it by mistake. You can even keep one band if you want, or you can select all the bands if you want. You can just choose what works for you. For now, we'll just do band 4, 3, and 2. Again, the more bands you select, the larger your download will be and the more time it'll take. So just remember that there'll be more pixels if you select all bands and your download will be larger. Finally, we select the output location where my GeoTIFF file will be saved. Click the browse button and I'm going to put it on my downloads. Just going to name it S2. And you can see my path is s2.tiff. You can also add a more meaningful name like S2 median composite that is just more meaningful. But again, you can give any file name that you want. So make sure you configure your download tool, select the image, scale 10 meters, selected the projection, map canvas extent, and then selected the bands we want to download. And once you're ready, click run. This is going to trigger the download. The Earth Engine API allows you to download 30 megabyte chunks from the servers at a time. So what the plugin is doing right now is it's going to figure out what's the total size of your data, and it's going to divide your data into small chunks of 30 megabytes each, and it's going to request each chunk one by one. If you're in a larger region, it might say downloading tile 1 of 10. And that means there are 10 chunks of 30 megabytes that you don't download one by one. I had zoomed into a fairly small region in Paris, so I have only one tile and which got downloaded pretty quickly. The amount of time it takes to download will depend on your internet connection between your computer and the Earth Engine servers. So If you're on a slow connection, it might take longer. If you have a fast connection, it's going to download pretty quickly. So for me, you can see it finished just a few seconds. I'm going to close this one. Now, since I've downloaded the data, I don't need this image anymore. I'm just going to turn it off. And I'm going to go and find this downloaded image in my browser. So I have this downloads folder, which is in my favorites. A pro tip for QGIS users: if you put your data somewhere always and you want to quickly find it, you can first browse to it and right click to add it as a favorite. And that will always appear at the top of your browser. So you can see here, I have this TIFF file that got downloaded. And if I load it here, this is going to load that image to QGIS. And now this is not WMS anymore. This is a real GeoTIFF file that lives on my computer. I can go and check this computer, and you can see this one is a median composite of 2.3 megabyte that was downloaded from Earth Engine. By processing maybe 30, 40 images for the year, calculating the median value at each pixel, and then downloading the result. Again, I didn't have to spend my own compute. Earth Engine servers did all the hard work of compositing. I just got the result. Now, once I have this GeoTIFF file, this works just like any other raster dataset in QGIS. So I can use any QGIS tools. I can build workflows that can take this as input and do some processing. You can see that this image looks slightly different than what we had visualized, even though we have the same bands. The reason it looks different is because QGIS applies its own visualization parameters. If you want the same visualization that we did before in Earth Engine, I can open the layer styling panel, and you can see there are red, green, and blue bands. You can see this is what QGIS has applied. I want to just change it to 0 to 3000, which is what I'd used previously. So if I change my min-max value from whatever QGIS determined to be 0 to 3000, now my image will look exactly how it was appearing when I loaded this data. So again, my data has the raw pixel values. If I inspect this, you'll see that these are the different values. It doesn't change the values. It just changes what visual you see that is a combination of these three values. If you want it to be a little higher contrast, if I make it 2000, you'll see the image will be higher contrast. You'll see kind of more brighter things. If I see it's too bright, I can maybe make it 4000 and it'll become a little darker. So you can adjust these parameters to create a nice visualization that you want out of that. QGIS by default applies a 98th percentile visualization. It'll compute the histogram and pick the value at the bottom 2% and the top 98th percentile, which usually creates a nice looking visual for you. Let's work on our second example of working with the QGIS plugin. In the first one, we learned how to load some data from any of the catalogs, load a layer, WMS layer that the plugin generates into QGIS, and then export that layer for a given region for a selected bands into a GeoTIFF file. Now, these tools that the plugin provides, they are also regular processing tools, and that means they are available in your model builder, so you can create a workflow and use them as part of the workflow. And this unlocks many use cases where you want to get data as part of your workflow, and instead of manually going and downloading data, you can use this in your workflow to say, hey, I'll configure the plugin to download the data for whatever region I specify, and then I'll be able to download the data. And the result is a model which can look something like this, where you have some parts that are using Earth Engine, and you say, here's a model that will fetch some data, export it to GeoTIFF, and then the result can be analyzed in QGIS, combining with other local data sets. And the end workflow will create a nice user interface, and the user of your workflow will not even need to know that what data you're loading, where are you getting it from. They just say, here's my region, here's the configuration parameters of what I want to do, click run, and the workflow will say, I will go and download the data, and then you can analyze the result. So we're going to learn how this works. We'll build a workflow to analyze land cover data. The first step would be to find a suitable land cover data. There are many, many data sets, so we'll go and review some of this data set that might be useful. We'll find a land cover data set. We'll download the land cover data for the chosen year and chosen region as a GeoTIFF file. Once we have this, we say we want to compute the land cover area we'll compute the area of each land cover in my region. So within my city or within my area of interest, how many hectares of urban areas, how many hectares of vegetation, and so on. I will compute area of each vegetation class. We can also do some conversion. We'll say we'll convert the area from square meters to square kilometers. And we have our results. And that means we'll be able to select any polygon in the world, run a model, and the output of the model will be just a table of land cover areas. And in the background, the model will do all of this processing, and we'll see how to set this up. And then we'll also run some validation. So we'll say how to add some validation. So the user specifies some value which are not acceptable or doesn't make sense for the workflow that we have. We should stop our workflow and not send the request to Earth Engine. Let's get started. What I want to do first is I will do this step by step first in QGIS without the workflow. So I'll just do each step manually, and you can understand the workflow step by step. Once we have the workflow and you understand how this whole thing happens, we'll then dive into Model Designer together, and then we'll do each step together. And we'll configure each tool, each step, and then build the workflow. So first, again, you can just watch and understand the workflow that we are building. So I'll do each step, explain what's going on, and then once we have this whole idea of the steps needed to get the final results, we'll go and dive into the workflow. For this section, we'll need some data that we have given to you in the zip file. You'll find the link to download the zip file in the course material. Once you have the zip file, you can go and unzip it. This one has just one geodesic file that we'll use for the first part of the section. And then there are a bunch of solution projects which will allow you to catch up to intermediate steps or see the output and what the final model looks like. So once you have unzipped it, you can either put it in downloads or somewhere you can find it easily. Let's go and load this bangalore.geojson in QGIS. From the QGIS browser, you can go and find the downloads folder, find the folder where we have unzipped this data folder, and then you'll find this geojson file. I'm going to drop it into QGIS. This is a GeoJSON file. GeoJSON file is like a vector layer similar to shapefiles. It can have multiple features. This one has just one polygon for the municipal boundary for the city of Bangalore in India. This will use that as a data set to kind of build our workflow. Once we have a workflow, you could use any polygon in the world, and you'll be able to get land cover information for that particular polygon. So let's say the question I want to answer is, what's the land cover area for different land cover classes in the city? What percentage of the city is green? How many of all the municipal boundary? What percentage is vegetation? What percentage is water bodies? And this is a kind of common thing that you will want to analyze. For that, you need to find a land cover data. So let's go and see our catalog of where we can see some suitable data set. I'm going to go to the Earth Engine data catalog. There are many land cover data sets available here. I'm just going to search for land cover. Here, the first result would be all data sets which have a tag land cover. So when they create a new entry, there are different tags. So you can easily find that even though the word land cover may not appear in the title, you'll still be able to find this data set. And you can see there are many data sets. There are some regional data sets. So this is the Canada crop land cover data. This is the European Korean land cover data. There's this data set called ESA World Cover, which is a nice land cover data set, which is for the entire world. There are two versions. There's a V100 and then there's V200. This is for year 2020, and this is the newer product for year 2021. Let's pick this one. So this is the ESA World Cover 10-meter data set. You can see the date range is 2021. So this is an annual product. So you have all images that were collected in this 1 year, they have classified them, and then you have a ready-to-use land cover product. So this one, if you see, there's only one band. So there's one band called map at 10-meter resolution. So when you open the data, you'll have one band of information. Each pixel is classified into one of these values. The table is also given here. So this is the legend that you'll see. If the pixel value is 10, that means it's a tree cover. So that's a vegetation pixel. That means that pixel was determined to be a tree cover used in this data set for that year. Similarly, there is cropland, grassland, built-up areas, and so on. And if I now have this data for my region of interest, I can say tell me the total area of all pixels with value 50, and I'll get the total built-up area. I'll say, give me all the pixels with the value 10 and sum up their area. I'll get the total tree cover for the city. So that's what I want to do. So I want to use this data set. There are many other land cover data sets. I want to show some of the other ones that you may not be familiar with. In the community catalog, there is a whole section on land cover. So there is a section on global land use land cover data sets. So if you're interested in global data sets, these are the ones. There are land cover data sets which focus on a single land cover, like global mangrove project. That means they're just mapping mangroves. So you get mangrove versus non-mangrove. And again, many of them are time series data set. The Esri one is also quite popular. Many people like to use it. This is a 10-meter data set that Esri created. You have land cover information from 2017 to 2024. So again, this is if you say, I want to know the land cover change in my region, maybe I'm working in an area where there's no existing land cover, you can pick this 2 land cover data sets and compute the change between those. There is GLC FCS, which is again a long-term time series derived from Landsat data, 1985 to 2022, 35 land cover classes, really nice land cover data set that you can use. There are many urban data sets. If you're interested in mapping impervious surface, urban versus non-urban, you can use this. One limitation of the global data sets is they may not be very good in your region of interest because their focus is global. Global models don't really have high accuracy in any one particular region. So maybe you want to pick regional data sets. There are many regional data sets that are available. Map Biomass is amazing in South America. They have amazing maps, very detailed. So if you're working in South America, maybe you want to use the Map Biomass one. NLCD is available for the US, really high quality land cover data set. And similarly, for example, for a project, I'd used the South African land cover data set, NLC, really nice, high quality data set, but limited to South Africa. So again, you can go and browse this catalog to find a good land cover data for your region of interest. For our problem of computing the areas of land cover, let's use this ESA world cover data. So we know that this has one band and you have band classified into these values. Let's load this into QGIS. Again, I'm first demonstrating the steps. We'll have to build this workflow step by step. So you need to first understand what steps we need to do. So again, just watch and understand, and then we'll do this together in the workflow. Before we load this, we want to pick a projection that we're going to work with. Since we want to compute areas, we see that my current layer is in EPSG 4326 and then the units are in degrees. That means if I computed area for this using this projection, my area will be all in degrees, which is not what we want. You can't really work with a geographic CRS when you're computing areas. So even before we load the layer, what the first thing we want to do is we want to reproject it to a projected CRS, which has units in feet or meters. And that means when we compute the area, we'll get the correct results. I'm going to reproject the layer. So the first step in our workflow would be to reproject the layer that we have loaded into a target projection. We can, for this one, we'll choose the UTM zone for this region. Again, we'll make this configurable in our model. That means whoever is running the model, they can pick what projection they want for their workflow. So they can pick the local UTM projection or another local projection that they want. So we're just going to reproject this layer. So I'm going to run this, and you can see my tool finished, and I have this reprojected layer. If I hover over it, I can now see this new layer has the EPSG code 32643, and the units are in meters. And that means in this projection, I should be able to compute the areas, and whatever area I compute will be in square meters, which will be the right results. Next step is to load the ESA world cover data. I'm going to use the plugin and add this image collection. If you read the documentation, this one, even though it's an image collection, there's only one image inside. There's one global image that they've created, and still it is just published it as an image collection. So we don't need to worry about filtering it. We just say, yeah, just create a mosaic. That means whatever the image is that will show up as the pixel value. We don't even need to filter by dates because all the images, or there's only one image for 2021. So you don't need to apply the filter. We'll select the current map canvas extent. We can also, if you don't want to do this, what we want to really do is we want to get data that covers our layer, the polygon that we have. So instead of doing this, what we're going to do is we say, compute the extent from our reprojected layer. And that means whatever layer we had selected, which got reprojected, we'll use the extent for this. And this is important so that, even if you zoomed out and your layer is small, you don't load data for the entire region. So we have calculated the extent from the reprojected layer. We have only one band called map. And we don't need to worry about min-max. If you want to put min-max, we can put here 10 to 100. Let's try this 10 to 100. But again, if you do this 10 to 100, we'll have to select ramp, which doesn't really make sense. But again, we'll just keep it blank. So it'll be the default visualization parameter. That's now I've selected doesn't allow me. Let's just do 10 to 100 and we'll do spectral. So again, this won't have the same color codes as the legend, but we'll see something on the map. Let's run this. And if your purpose is just to download the data, visualization doesn't really matter. Even if you get something that is totally black, doesn't matter, because when you download the data, you'll get the actual pixel values. But again, you can see here, we have this land cover data. How to interpret this? Well, we have different pixel values. So if I use the identify tool and click somewhere on the image, you'll see that the Earth Engine server will send the pixel value. In this case, the pixel value is 50. And I wouldn't know what is 50. That is built up. That means that pixel is classified as a built up pixel. If I click somewhere, which is probably a water body, so this looks like a water body. If I click on it, it should be a different value, which will be the land cover value assigned to water at that pixel. And you can see this is 80, and 80 is permanent water body. So this is how the dataset works. We have the land cover data that was displayed from this Earth Engine layer. Let's just download it. So I'm going to go and download it as a local layer. Let's export this. The native resolution is 10 meter. Again, we're going to use the projection that we set for our input layers, which is the UTM zone. Earth Engine will reproject it and send me the pixels in this position. And that is important because now I have a layer which I can compute the areas from directly. Our extent will again be the reprojected layer. We'll use the bands here. And then I'm going to save this as a file. So this is going to go and download the data as GeoTIFF file. When we're doing the workflow, this file, you can choose to save it, or it could be just an intermediate temporary layer that will just go away after your workflow is done. If you're not interested in the actual image, what you're interested in is just the area. So once the area is computed, you don't really need the data. Okay, don't save it in the workflow. When we're running this, we have to save it, so it's going to land somewhere on our computer. The export finished. I'm going to turn off my layer and load the data that was just created. So this is the land cover data set. So this is the local land cover layer that we loaded. I'm going to layer the projected layer on top. We have the raster layer with the actual pixel values. You can see I can now click around and see the pixel values, but I have a lot of pixels outside of my region of interest. The plugin doesn't allow you to clip it to a specific geometry. You can only clip it to the extent of the layer. But we can use, since now this is just a GeoTIFF file, we can use QGIS to clip it. So I'm just going to use this tool that is available for raster layer called clip raster by mask layer. And I'm going to say, take my land cover data and clip it with this data. Here, the important thing is both the projections should match. And so the clip happens correctly. So make sure we select the land cover data, which is in the UTM projection. Also, we select the reprojected layer as a clip layer. Let's run this, and QGIS is going to clip and remove the pixels which are outside of our region of interest. And now we see that we have this raster layer that we downloaded from Earth Engine, and we have clipped it to this area. We just want to know what is the area of different land cover classes in this. If you want to compute areas of raster, you can use the built-in processing tools. The name of the tools are not very intuitive. So a pro tip is just search for what you want to do. So if I say raster area, you'll see all the tools which mention that it can do something with raster area. The correct tool for our purpose, where we have a raster and we just want to compute a value for each unique value, that tool is called raster layer unique values report. You would have never guessed it if you're just looking for the tool, that this tool computes the area of each pixel. So again, just search for what you want to do. If you have multiple polygons, let's say I have multiple cities, or I have admin1 polygons, and I want to compute the area of different pixels in each of those polygons, the tool is raster layer zonal stats. So this is tool for multiple polygons. This is the tool. If you just say I have a raster, give me the overall value of the layer. And since we have clipped it, this will be the area of the land cover in our region. Let's run this tool. We have a clip layer. By default, when you run the tool, there are two outputs that you can generate. You can generate a report, which is just an HTML file showing what are the different areas of different pixels. What we want is the table, which is a tabular data that we can save to our disk. By default, this says skip output, so it won't be created. I'm going to change it to say create a temporary layer. And I don't want a report. I can just skip that output. Let's run this. So I get this new table that got created. If I open the attribute table, you can now see I have a table that says in this raster that you selected, the pixel value of class 10, this is the total area in square meters. The area of water bodies with class 80 is this many square meters. So I was able to compute the area of each pixel. And again, if you're a QGIS user, you probably know how to do this. If you're an Earth Engine user, unless you are a really advanced user, you cannot do this very easily. In my Earth Engine class, I spent like an hour teaching how to compute area. And that also after we covered a lot of ground. So again, this is something that is fairly easy for GIS people to do, but fairly hard for people who are using Earth Engine. And now we are able to use the tools in QGIS to be able to say, just get me the data. I know how to do my analysis in QGIS. I'll use the tools that I'm familiar with. So we can just convert this. So the last step we want to do is, this is in square meters, very hard to interpret. Let's just use the QGIS's field calculator to convert this into square meters. So I'm going to create a new field called area square kilometers. We have our field called meter square that was generated. And again, this is important when you're building workflows. It's useful to run through the process once, so you know what you expect as your data structures. Because when you run the workflow, when you're building the workflow, you don't really know what will be the field name. So it's useful to kind of do this step once manually, so you know what are the different data sets that are generated, and then you can know what to enter in your workflow tool. And we can divide it. So this is in square meters. We want to convert to square kilometers. So we have to divide by 1,000 times 1,000. You can also write it shorthand. This is 1 followed by 6 zeros. You can write it as 1 is 6. So this is the scientific notation, 1 followed by 6 zeros. Let's run this. Now we have this new layer, which has this new field, area in square kilometers. So now I say in the municipal boundary of city of Bangalore, we have 140 square kilometers of tree cover. We have 7 square kilometers of water bodies and 435 square kilometers of built up area. Right? So I was able to compute this using the built-in tools that we have, using the data from land cover. We're going to go and put all of this in a workflow. And that means instead of this city, if I just load a different polygon, I can just click a button and get this table created for me without me doing each of the steps manually. Now that we know what are the steps we need to do our workflow, let's go and start building the model in QGIS. We'll start a new project. So we're going to start fresh. And I'm just going to load this bangalore.geojson file. If you're following the course material, we are now going to start on section 2. We'll start the steps that are available from here, section 2.1. We'll go and follow each of the steps to build the model. The first step is to open the processing toolbox, and the model designer is accessible through this menu. So there's a processing toolbox menu. There's a first icon with some gears in it. Click on it and say create new model. So now we are doing the hands-on part where all of you need to follow along and do this on your own computer along with me, and we'll try to build the model together. Once you click this button, create new model, this is going to open a new window, which is the model designer window. Here, this is a visual tool where you need to drag and drop different components, join them together, and that will build the workflow. This dialog is kind of a mirror image of a QGIS. You have the canvas on the right and your algorithms on the left side, which is your processing toolbox. We'll start by naming our model. So I'm going to go and enter a name of a model. To name it calculate land cover statistics. This will be the name of the tool that appears in a toolbox. So once you have a model to run it, you'll have to go and find this tool here. Once we have the name of the model, go and click Save button. It's going to ask you the name of the model to save. Do not change the directory. It's going to save it in a special directory. This directory is in a profile folder. And there's a special place where QGIS saves all the models. So when QGIS starts, it loads all the models. If you would save it somewhere else, it won't appear by default in your toolbox. We'll name this Calculate Land Cover Statistics. And since I already have a model with the name, I'm just going to name it V2. It's important to save your model. It often happens that if you do something wrong while building the model, it's possible that your QGIS will crash, or when you run it, do some wrong configuration, your QGIS will crash. So make sure you don't lose any work after we do each step. I'm going to remind you to save your model. So you can always start from where you left off. The way models work is you need to decide what inputs are configurable and what parameters are static. That means they are hard-coded. In our model, what we want to do is we want to allow the user to select the input vector layer. That means they can load any polygon and we'll use that polygon to compute the land cover statistics. So one of our inputs that we want to specify as the model is the input vector layer. So there's a tab called inputs here, which will go and find inputs. There are different inputs you can have people specify. The input that we want is the type of vector layer. So I'm going to switch to the input tab, use the vector layer, and drag and drop it into the main canvas. This will ask me what is the name of the parameter. So name it input vector layer. There's a bit of validation also available. So you can enforce certain data type here. So you can say the layer that the user should select has to be of type polygon. And that means if the user has a point layer, they would not be able to select here. So it's a good way to enforce certain data validation at the type. The input can be optional or mandatory. We say we need you to specify a vector layer that we want to use. So we'll say the name of the input is input vector layer. The geometry type is polygon, and it's mandatory. Once you're done, click OK. You should see a nice yellow box. In this interface, the yellow boxes are inputs. The white stuff are the processing steps, and the green boxes are outputs. So we have an input to our model. That means when we run the model, the user will be able to pick what vector layer they want to specify as the input. Remember in the workflow I showed, when you want to compute area, that is highly dependent on the region that the user is trying to do. So we'll also want to pick a CRS, but we don't want to make the decision for the user. Let's say you're running this in Brazil, the CRS that is appropriate will be very different than you running this for India. So we also want to let the user pick the CRS that they want to use for computing the area. So let's use another input. There's another input here called CRS, which will allow to pick CRS. Let's drag and drop it here. We'll have the description projection for area calculation. There is an option to specify a default value. Since we are going to test this for the shapefile that we have, we're going to test this for the vector layer we have for Bangalore. I'm going to specify the default as EPSG 32613. It's just a default, so you don't have to pick every time. But if you say, I don't want to specify this, you can pick any other default that you want. And you can just click here and search for any other projection that you want to use as default. We're going to use this code 32643, which is the UTM zone for where the city of Bangalore is located. So I'm going to use that as the projection. Let's click OK. So now we have this another input that we have specified, which is the projection that we want to use for all our calculations. And this input will be used for our reprojection step, for requesting data from Earth Engine. All of the steps which require a projection input will say, use whatever the user specified. And that means my tool is now more versatile. I can drag and drop any polygon layer and select any projection, and I get my output in the most accurate area computation unit for that region. Save your model. Let's do the first step. So the way you do this, you say, I have these inputs, I want to do something with them and generate some output. You can drag and drop the algorithms. Let's go switch to the algorithm tab and search for the tool reproject. There are many reprojection tools. There is one for raster, vector. If you have a newer version of QGIS, there'll be one for point clouds. So make sure you pick the tool that is under vector layer, since we are dealing with vector layer here. So drag and drop this here. You can also double click it. It will do the same thing. This is a configuration for the tool. This looks similar, but slightly different. Here in Model Designer, when you're specifying and configuring your processing tools, you have different options on what to use for each parameter. What should be the input layer that we are reprojecting? Well, that's the model input. So whatever the user has picked for our polygon layer, that's the one we want. What's the CRS that we want to reproject to? Well, we say don't use a static CRS. We are making it dynamic. Whatever was picked as a CRS, we should use it. So for this one, we're going to click on this 1, 2, 3 button and say don't use a static value. Let's use one of the model inputs. So I'm going to switch this to model input, and then I'm going to say select this one. So whatever projection was selected as an input, that would be the one that will be used to reproject the layer. Here, the last time it says enter name if this is the final result. Let's say you have a workflow with 10 steps. You don't want to load all intermediate layers. Just say, I don't really care what the layer looks like. I just want the final layer. You can skip entering the name. What if you enter a name, that layer will be generated and loaded into QGIS. While you are building the model, it's always useful to test whether you configured everything right. So when I'm building the models, I always enter a name and just check my output, whether the model worked as expected or not. So I'll just name this reprojected. Well, remove this later on because that's not the output that we're interested in seeing. But right now I'm going to enter this here. And as I click OK, you see that I have some arrows that are flowing from my inputs to this first step of my model, which is generating an output called reprojected. Let's go and save our model. So here we have a first step configured. Let's save the model. Once you saved it, we can test the model. It's always a good idea to test each step. So I'm going to test it. I'm going to click this play button, which will run the model. The model will just look like a processing tool. Here it says, what's your input vector layer? What's the projection? And you can see we had selected this as a default. So it got selected and my input vector layer is selected. Let me just run this and see if it works successfully. It worked. We got our reprojected layer here. If I hover over it, you see the layer projection is 32643. So that step worked correctly as I expected. The advantage of a model is now if I run the same model and say, no, I don't want this projection, I want 3857. I can just run this and my model should generate another layer, which is in 3857. So that's the advantage of having the CRS as a selectable parameter. So whatever we specify as the input will be used internally for each step. We know this works, so we can just remove this output. So we can open up the tool and say, I don't want this layer to be the final layer. I don't want to open this. I can just keep it empty and this will go away. Also, I can just click this cross and say, I don't want this output because this is an intermediate step. I don't want to see it. So that's fine. So we have our reprojected layer as an intermediate step. Next step, let's load our land cover data from Earth Engine. So the next step is to fetch the ESA world cover data layer from Earth Engine and load this into QGIS. We're going to switch to the algorithms tab. And since we have the QGIS plugin for Earth Engine installed, we have those tools available here as well. Let's drag and drop the add image collection tool here. Here we enter the image collection ID. Here we're going to make it a static ID. That means we always want to use this particular data set. If you wish, you can also make it an input saying that enter the ID of the land cover data set that you want. And that is more flexible if you choose to do it. You can also have a drop-down saying these are the 5 options you can select from. There's an input called enum, which allows you to specify list of IDs or list of values that you can pick from. So if you say, I will support this 5 land cover data sets in my model, and you can just enter those if you wish to. But right now, we're just going to keep it as static ID. So we're going to use this ID This ID is given in your step number 7. So if you are following this material here, you'll find the ID here in step number 7. So you can copy this ID, which is the ID for the ESA bulk cover. Next, we need to specify the extent. Remember, we will always want to use the extent that is computed from the reprojected layer. That will be the extent of the region that we want to compute. So here, instead of a static extent, we're going to say this would be the algorithm output, because the reprojected layer was generated in the intermediate step. It's not one of the inputs that we want to use. So we say, switch this extent to an algorithm output and use the reprojected layer. So the extent will be computed from the reprojected layer here. Now you get the hang of how to configure each parameter. So let's try the CRS. What CRS do we want to use? Well, the CRS is whatever we chose as the model input. So this was the projection that the user has selected, and that's the same CRS for our input. The next step, property filters. And again, the model designer has a limited interface where you can't do all the stuff that we could do in the main processing tool. So here it says, if you want to specify the filter, you specify in this format. You can just specify it as a key value pair separated by comma. We don't have any filters for this. I'm just going to remove this text here. So make sure it's deleted. We also don't want to specify the date filter, so we can keep it not selected. The compositing method should be default mosaic, should work fine. And finally, visualization parameters, again, the same thing. To specify this, we need to specify them as a JSON dictionary with key value parameters. We don't want to specify any visualization parameter. We're not even interested in visualizing this data. We just say, whatever is the data, we just want to download and use it. So let's just delete this visualization parameters, and then we'll keep the clip to extent as yes. Note that there is no option to say enter this name if it's a final layer or not, because this tool by default will always load the layer into QGIS. The way it works is it has to load this into QGIS for it to be available for the next step. So there is no option not to load this layer into QGIS. So that's why you don't see the option here. Let's click OK. And you should follow the arrows here to make sure you configure it correctly. So this tool depends on the reprojected layer and this input for the projection. Let's save the model. Let's run it and see if this step was configured correctly. So I'm going to run this. All we specify is the input layer and the projection. We're going to just use the 32643 that we had set as default here. This, even though the tool says there's no output generated, our Earth Engine tool for add image collection will load the layer into QGIS. So let's run this and see if everything works fine. You can see right now it's running the step 2 of the workflow, which is sending this parameter. And you can see now in QGIS, it got this layer added. I'm just going to jiggle my map slightly to force it to load the tiles for this region. And it is loading this land cover data for the region. So again, this was, once you've done this, you can just run the tool. You don't have to do this configuration every time. And that means if you build such models for your team, the team really doesn't need to know anything about Earth Engine or plugin. They say, here is a tool, I can run this and it'll give me the output. So again, you can kind of build these workflow tools for even yourself where you are doing this often. You say, I don't want to go and configure this tool every time. I can just have a model that automates my workflow. We'll turn this layer off and go back to my model. Let's do the next step and download our GeoTIFF. I'm teaching you the way I build models. I always add one step, check the output. Even though I've been using QGIS for 20 years, I still don't trust myself to build 10 steps and make that will work correctly. So don't do this yourself where you say, here's a complicated 10-step model. Don't do everything at once and test it. You'll spend hours debugging if something goes wrong. Always add one step, run it, check the output, and that's a good way to kind of build it and catch your errors early. Otherwise, you'll spend a lot of time just debugging your models. Let's do the next step. The next step is also from the Earth Engine plugin. So I'm going to drag and drop this export image to GeoTIFF tool here. It's asking me the image name. Now this image name was generated, the Earth Engine image was generated in the previous step. So we say it's not a static value. It was an output of the previous algorithm. So if I switch to algorithm output, you should now have an input that you can select that this was the whatever the layer name that was created from this image collection tool. Extent, again, for the extent, we are always using the reprojected layer output. So we switch this to algorithm output and use the reprojected one. Scale, we're going to hard code the value. We know we have hard coded the dataset ID. That means we know the resolution that we want is 10 meters. So we're going to use the static one. If you had made it more dynamic, you can also have one more input as a number input from the model saying that please enter the scale that you want. And you can use that in your model here. But since we know it's going to be 10 meters, we can hard code this here. The projection, again, the projection, we always use the input projection that we had selected. So whatever data we're requesting from Earth Engine has to be in the projection that was specified as input. And here we want to specify the bands to export. We know that there's only one band called map with a capital M. So specify that as input. If you skip this, it's going to download all bands and you'll still get the map band, but it's useful to be explicit and say, this is the band I want here. Make sure the M is capital here. I'm going to name, just to test my model, I'm just going to name it output and click OK. And you can see my model is getting a little more complex now. And I have this output here. We save the model and let's test if this step was done correctly. We have the same input. I'm going to save this to the file and we're just going to name this land cover from model just to differentiate it from the other land cover file we have. Let me run this and see if I'm able to download the file automatically using this model. One of the most difficult parts of testing this plugin was to ensure it handles the projection correctly. There are so many different ways to specify projection. There'll be your projection of your input layers, projection of your intermediate layers, projection of the Earth Engine input layers, projection of your output file. You could have your project set to a different thing. You will have two layers in different projection, and plugin has to understand and do the correct thing. And there was numerous bugs that I found during the testing phase. And I'm fairly confident that it handles all the edge cases. So again, projection handling is something that's we thought through carefully. And again, I recommend this approach where you say, take projection as an input and always use that. So you're consistent in how you specify the projections everywhere. So here we have done the first 3 steps of our model. You can see these 2 steps are part of the Earth Engine workflow. So I'm going to just organize it a little better. So it's easier to see what parts are Earth Engine and what parts are using the local QGIS tool. The next step in our workflow will be to clip the downloaded raster to the reprojected layer. So let's bind and drag the tool to the canvas. So we'll search for clip and we're going to pick this layer, pick this algorithm in the raster extraction. This is clip raster by mask layer. The layer that we want to clip is generated in the previous step, which is the output file that we had saved to GeoTIFF. So right now we are out of Earth Engine world and now we are in the QGIS world where we have this local GeoTIFF file that was exported in the previous step. It said, take that file, which was clipped to the bounding box, but we now want to clip to the actual geometry and we want to clip it with the reprojected layer. And again, both of this will have the same projection because we ensured that we specified the chosen projection for both of these so that will match and the clip will work correctly. Sometimes if these 2 are in different projections, your clip will not work correctly. Rest everything can be left as it is and you can click OK. We don't want to test this step. If we test this step, it's going to again download the GeoTIFF file. It's going to spend a few minutes. So at this step, we say now my GeoTIFF file download is working fine. I'll do the next few steps and then test the final output. Click OK. And you can see now I have this clip raster by mask layer as the next step. In this one, the only two things we had to change was the input layer and the mask layer. Everything else can stay the default. Both of them should be algorithm output. The first one will be the output file from export image to GeoTIFF, and the second one should be the reprojected layer from the previous step. Save the model. The output of this will be a clipped GeoTIFF file for our chosen city boundary. And now we are ready to compute the area. So we're going to run this tool, which is used for computing the area for each raster. This tool is called raster layer unique values report. Let's drag and drop this tool here. Here, the layer that we want to compute the raster is the one that was clipped in the previous step. So I'm going to change it to algorithm output, and we'll use the clipped layer. And I want to test the result to see if it works fine. So I'm going to enter the name for the table. Just going to name it as a table here, so I can see the output that was generated here. We'll remove this because again, this is not the final output. We'll also have to do some post-processing on this. But for now, I want to make sure the previous two steps were correctly configured. So I'm going to enter the value table for this unique value table and click OK. If you're building models which are a little more complex, it helps to organize them as you kind of building them. Otherwise, there'll be a big mess of spaghetti arrows going from everywhere, and it's hard to debug. So again, good to keep it organized in kind of a logical sections so that you can know what is going on here. So once we have configured this, let's test our model to see if the layer is still generated. So here by default, since this one is skip output, I'm just going to say create a temporary layer. And now when we run this, it should now download the data, clip it, and generate the table. So once the model ran, it loaded those two rasters. I'm going to turn this off, and this is the table that was generated. And if I open it, you can see this is the same values that we expect for this region. So the table was generated successfully. For the next step, we want to add a new column called area square kilometers, which is dividing this value by 1000 times 1000. So we can convert this from square meter to square kilometers. I'll remove this all layers and go back to my model. So we tested this and this worked fine. So I'm going to remove this as an output. And now we're going to add one more step to create our final output. Let's go and select the field calculator. We'll take this. The table that we want to use was generated in the previous step. And this will be the unique values table that was generated from this raster layer unique values report. So to take that, we want to create a new field. We'll name this field as area underscore square kilometers. Decimal type is fine. Here we have to enter the expression. When we did this in our main QGIS workflow, we were able to pick the field from here. Right now, you can't really pick a field from here because the previous layer doesn't exist yet. It's, the model is not run, so it doesn't know what would be the field. So that's why it's important to run this first when you do in QGIS and say, what is the field name that we expect here? And we know that the field name we expect is M2. So we'll have to kind of know that to be able to enter the formula. We can't really pick it because the layer doesn't exist yet. And we'll divide it by 1/6. And this is our final table that we want to see in the output. So I'm just going to name this as class areas. Here in the field calculator, we are using the unique values table as the input layer, adding a new field called area square kilometers. The formula is double quotes M2. In QGIS expression, double quotes refer to a field value. So make sure you use double quotes. If you do single quotes, that will be interpreted as a string, a text called M2. So double quotes M2 divided by 1/6. And we enter the name as the class areas. Let's click OK. Let's arrange our model a little bit better so we know what is the flow here. Save the model. And now we are ready to test and see if the whole thing works correctly. Let's test it. We'll keep all the inputs the same and we're running it. If everything goes well, we expect to see a table with a column called area square kilometers with the area for each land cover class that was calculated from the ESA world cover data, clipped to this region, and was computed using the QGIS algorithms. my algorithm finished, and I have a table called class areas. Let's open it up. And now you see that I have my final layer, which is the area square kilometers computed from ESA world cover. We have our model that is saved on a computer. So if I want to run this model again on a different data set, I can open the processing toolbox, and the model will appear in my models section here. And here you can see there is should already be a tool called calculate land cover statistics. And I can just click and run this like any other algorithm in the toolbox, and it will be available. Now, this model lives on this computer. What if you created this model on your work computer and you are home and you want to run this model? The model is sitting in that computer in your office. Or maybe you want to share this with your colleagues and say, hey, here's a model. What's a good way to kind of share this model across easily? What I recommend is when you have your models, most of the models are specific to certain projects. So let's say I have this QGIS project with this data layer loaded. I can save my model inside of this project file. In the model designer, there is this option here. The third option, save model, will save it to the computer, which is what we've been doing so far. But there's the option here which says save project, save model in the project. Go ahead and click this button. If I save this, this says the model was saved inside the current project. And after saving the model, go back to QGIS, and you'll see that there's a new folder here called project models. And if I expand this, you can see my model is here. And that means now if I go and save this QGIS project, which will be saved as a QGZ file, if I send this QGZ file to somebody, they will have the model. The model file is embedded into the QGZ file. And that means wherever you open the project, your model will always be there. And that's a really nice way to save, backup, and share your models. I'm going to save this project. So in main QGIS window, I'm going to click save, and it's going to ask me to save the file. And I'm going to just say my land cover. So now I have this land cover QGZ file. Whenever I send this QGZ file to somebody, they'll be able to open this up, see what the layers are, and they'll always have this project models folder, which they can use to run the model on the dataset. If you want to catch up to this point, we're going to continue and improve the model a bit, but this is a good point to just have a model, test it on your workflow. If you have built a model on your own computer, please test it and see if it's able to run successfully. If you want to just catch up to this point, in your data package that we provided, there's a solutions folder. If you open up this project, model designer checkpoint 1, open up this project. It's going to load this pre-configured project where we have this layer, and in the project models, we have the complete. And this model is editable. So now if you want to see what this model looks like, I can right click and edit the model, and you can see the model that is available here. So if you just want to try out the model, open up this solutions project, model designer checkpoint 1, find the project models, open up the saved model. You can double click it, select the provided layer as an input, select the projection, and then run it. And that should run the whole workflow, and you can test this with your data. I want to test this with a different layer. So I've downloaded another GeoJSON file. This is for a different city. This is the city of Chennai in India. And now I want to know what is the land cover distribution for this region. And this is a different region altogether, but now I can just compute it. So it could be any shapefile or any layer with a single polygon. The restriction we have is single polygon because we are not, the workflow that we designed doesn't work with multiple polygons. So any file with one polygon, I can load it here. I can say calculate land cover statistics for this region. This is my input layer. For the projection, since I'm in India, there is a national projection. So I don't want to use the UTM projection. I want to use the national projection for India, which is EPSG 7755. And this is the India National Spatial Foundation projection, which is the recommended projection to be used for India. So this works for all cities of India. So I would just want to use this one. And I'm going to run this. And now you can see the power of the plugin plus the workflow that I can now go and compute this anywhere in the world the data comes from Earth Engine. I can use all the QGIS tools and algorithms to compute and do analysis on them. And then the model design allows me to be flexible and choose whatever projection I want, whatever input I want, and it just works. And you can build such tools for yourself or for your teammates to use and work with different data sets. While this is going on, you might be thinking, where did I get this data? If you're in India, getting data is always a challenge. So I want to share some of the data sources. The one place I always look for data for India is this place called Data Meet. This is a community of data science enthusiasts. It's a forum, so you join the forum and just search the forum. People would post all kinds of data set. People ask like, I need this data for this region, and somebody would find it and share it. So the one that I'm using it is for this spatial data of municipalities. And if I go to, this is the GitHub page, and they have this data for all different cities of India that they've collected. And the data that I'm using comes from this place. It's again, open source collection of boundaries for different cities. You can see my processing for Chennai finished. And if I open the class areas, you can see I have different results. And this is the result that I computed for the different class areas for a different city altogether. Let's continue. I'm going to start from the Checkpoint 1 project. If you want to catch up to this point in your data package, we have the solutions folder, and I'm starting from the Checkpoint 1 project. This is as the project models folder where we have the model that we built so far. I can right click and edit the model if I want to jump into model designer. If I just want to run it, I could just load a different shapefile or different vector layer and just double click to run the model. But I want to improve the model, show you some advanced features of the model designer. So I'm going to start from here. The first thing that I want to do is we want to add some validation. One of the things that we have made a choice here is for computing the area, we're going to use this tool, raster values unique report. This tool says, give me one raster layer. I'm going to give you the aggregate sum of pixels in the entire raster. And this kind of workflow works because we have only one polygon in our input layer. So we get data for that extent, clip it to that polygon, and then get the area. If my input layer had, say, 10 polygons, this workflow doesn't work. When you say clip by mask layer, you'll get the data for the entire bounding box of all the polygons. And then this area will just be a single area. If you want to compute area for individual polygons, there's a different tool that we should use, which is the tool that we use for raster area called raster layer zonal statistics. This tool can allow you to compute areas for multiple polygons. But since we have built a model that doesn't support that, by accident, some user might select polygon layer which has got more than one polygon. So I want to show you how you can add user validation, where you can say, I don't want this model to be run unless I can meet certain condition. And that's a useful way to learn how to add validation to this model. So let's do this. What I want to do is I want to load some other layer which should not work. So I have this other layer. So let's say I have this layer of all the admin 1 regions of the world. And you can see it's a very large data. If I just run my model will allow you to select this. And if I run this, bad things will happen, right? First is go download the data for the entire world at 10 meter. And even if somehow that worked, I'll just get area for the entire world, which is what I don't want. So what I want to do is I want to stop my model saying that this is not correct. You should not be specifying this as input. You should be selecting this as input, which has got one polygon. So let's see how we can add this. One option is there is an expression here. So I'm going to show the QGIS expression engine. There is a function in QGIS expression engine called layer property. This is a very useful function if you want to check certain values of the layers. The way the function works, you give the layer name and the property that you want to check. And you can check the name of the layer, title. If you had just got some metadata, you can check that. You can check the CRS of the layer. There's also a thing called feature count. So what is the feature count? How many features does it have? What's the path? This feature count is helpful for us to know if the feature count is 1, then only we should run the model. If the feature count is greater than 1, we should not run this. Let's just test this model. So I'm going to test this on this layer. and say, what is the layer count here? Or feature count. And you can see the preview says it's 1. That means this Bangalore layer has only one feature, and that was computed using this expression. I can also use this as the layer name. So if I just copy my layer name here, so I'm going to copy the layer name and go back to this. And say if I use this as an input layer, it says there are 4593 features. So now if I run this expression and say, check the value of this expression, and if it's greater than 1, stop my model. So I want to add those conditions. And again, this is a demonstration of how you may use this in your model. You can use it at the start, or you can use it somewhere in the middle. Let's say your workflow is running. At some point, you say, at this point, if you have this value greater than this, stop the model. Right? So again, this, or maybe throw an error message or throw a user information message or so on. The way we're going to do this is we will run this tool. There are certain tools that are available in the modular only. So there is a modular only tools. This section of tools is not available in your main processing tools because these are available, make sense. These tools make sense only in the context of the model. There is this tool here called calculate expression. This is specifically designed to evaluate a specific expression at a desired point in time. So you're running the model and say, at this point, I want to check this expression and get the value. So I'm going to bring this model in. So again, if you're following along, we are starting from the model that we have. Go and find this tool, calculate expression under the modular tools, and drag and drop it here. It's going to ask you to create the expression here. We're going to use this button to go into the expression editor so to create the expression. So this one has only one input. You can input the expression if you want to build it. We can use this dialog here. This will give us the expression editor. And the expression that we want to use is called layer property. Now, what's the layer name that we want to use? Again, this is something that we don't know yet, right? So that's the reason we use this expression editor to say, here are all the inputs that are available to us at this point in the model. So you can see there are a whole bunch of inputs available. There's a variable here called input vector layer. This starts with an @. So this is a variable. That means this variable will contain the name of the input vector layer that was chosen by the user. So again, this is not a static expression. This will be dynamic. This variable will have the input value of the layer that was chosen there. And what we want to check is the feature count property. Right now, you won't see the output because this layer doesn't exist yet. We tested this expression before, we know it works. So we just run it. And when we actually run the model, this will be evaluated. If you're following the course material, we are now following the course material. We are in section 2.2, and you will find the final expression that we are using here in step number 4. So you can just copy it from here and then paste it here. So now I have this calculate expression. I'm going to move it aside so I can see it aside. Now when I run the model, this expression will be evaluated. So when I run the model, this expression will be evaluated. We want to do something, right? We say if the model if this output is more than 1, if there are more than 1 feature, stop the model. How do you stop the model? If you look under the model tools, there are a bunch of other options you have. There's a tool called raise exception. If you ever run a processing tool and see this red error messages, those are created by this tool. So these are the kind of errors messages. You can also raise a warning. This is like, hey, I know something happened. You may want to think about it, but it won't stop your model. You can also raise a message saying that, hey, I found this many features. It doesn't really have to stop the model. It just says information message that appears in the log. But we want to stop the model in case that we have the value that is more than 1 feature count. So I'm going to drag and drop this tool here. It's going to say raise the exception. What's the error message? I'm going to say the error message should be the input layer has more than 1 feature. That's my error message that I want to say. What's the condition? Here, I want to say my condition is to be that whatever expression we had entered, the value of the output should be 1. So I'm going to change this to be pre-calculated value. So I change this to the pre-calculated value here, which allows us to specify an expression. And then I'm going to click here And these are all the different variables we have. We have this one variable here, calculate expression output. So this is the output of the previous step where we checked how many features are there. If it is one feature is great, we say if it's greater than one, this is the expression you should, if this evaluates to be true, you should stop the model. If you're using the model that we have given in our checkpoint project, this variable name should exactly be the same. So you can just copy paste it from the next step here. So here is the expression. You can copy paste it here. Make sure to change this to the expression here. Now my model, when I run the model, it's going to check how many features the input layer is, whatever layer I've selected, and raise an exception in case there are more than one features. There's one problem, however. When I run the model, what path the model will run? You can see it will, should it reproject the layer first or should it check the expression first? Those both are parallel. And that means this might happen, this whole branch will get executed before even this has worked. So here we have to say, no, please check this first. Only if this is correct, go and run this tool. And that is specified using dependencies. So we say, before running the very first step of the model, this step has a dependency on this step being evaluated first. So I'm going to double click this reproject layer. In the reproject layer, at the bottom, you have this dependencies section. And I'm going to click this and say, which are the other steps that this should depend on? And we say both of these. That means both of this have to run before I can run this step. If I do this, those two will run only if the exception wasn't raised, this step will happen. And this will ensure that if my input layer had one polygon, my model will run. If it is more than one polygon, the expression will return more than one and the model will stop. So select both as dependency. And now you can see my model flow has changed. It will go here first, and then only after these two are evaluated, the model will continue to start. Let's test this model. I have this layer, which has definitely got more than one features. If I select this and run my model, you can see it stops. It says the layer has more than one features. This happened because it evaluated the expression, which was more than one, and it stopped. I'm not changing the model. I'm just changing my input to this other layer, running it. And you can see this was one value, one feature, and the model continues. So now I have added this dynamic error validation where depending on the user input, my model will either run or stop and do the correcting on the context. Even if you haven't been able to keep it up to this section, is fine. I wanted to let you know that this options exist, and this will be helpful for you as you build your workflows. And this is something that I've not seen documented anywhere. Most people don't know that this model tools even exist and how you can use them in your workflows. I want to share a few more tips on working with the model designer. One of the things that I'm very particular is when I build my models, I want my models to be self-documenting. That means I don't want to explain what it does. The model should explain itself. It's also a good practice for you to kind of organize a model. If you're building it for others, it's a requirement because then others should be able to maintain and understand the model. Even if you're doing it for yourself, if you have a very complicated model, organizing this, documenting it will help you maintain it much better. So I'll show some of the tools that will help you with this. One of the things that I like to do is I somehow don't like this boxes to be misaligned. I want them to be a nice straight line. There's a nice tool here. If you can select the couple of boxes here in the model designer, there is an edit, snap selected components to grid. If you do this, it'll just align all of the boxes. And again, this is something that if you have lots of steps in your model, it just makes it nice and clean. So I'm just going to align this 4 as well. Let's do snap selected components to grid. This one also, I'm going to align both of this together. It's just a small thing, but it's quite helpful as well. Another thing you can do is you can document what the different sections are doing. The model designer has this option called add group box, which allows you to draw a box around certain components and document it, what that means. So I'm going to add a group box and say I'm going to have a new group here. This is just visual. There's nothing going on internally, just for your visual assessment. I'm going to add a group here and say this one, all are in Earth Engine. And I'll select this color to be blue color. So you can see now I have a box around here. It says these two stuff are the steps that are happening in the Earth Engine. So when you look at the model, you can say this is the Earth Engine part. Let's add one more box here. I'm going to add another box here. And we'll say this is the stuff that's happening in QGIS. We'll edit the box and maybe we'll put it as a green color. So this part is happening in QGIS. You can see it's now displayed here. So I can say, hey, these are the stuff happening here. And finally, I have this validation part, which I have those two steps here. I'm just going to add a box around it here. And I'm going to name this as validation. So now you can see my model looks much nicer. If somebody opens this model, they know exactly what's going on. They can see the workflow. And again, if you send it for a client or for the users, they'll have a much better understanding of what the model does. And I can go and save it back to the project. So now my project has the updated model. If you want to test the final model and get to this one, we have the checkpoint project available in our solutions folder. I'm going to go and open up the checkpoint 2 project. And here is the model that is available in your project models. If I open up the model, this is the final model that we have built. And if you have your own data, you can test it with that. Try to load a layer with more than one polygon, and model should raise an exception so you can see how it works. If you missed a step and you want to repeat it, you can go and follow the workflow. We have documented everything step by step. This is the end of the material that we have for the workshop. But I also want to show you some other things you can do with the plugin. This particular workshop is focused on QGIS users who want to get data from Earth Engine. But if you are an Earth Engine user, you can actually do some more things with this plugin. So I will show some demonstration and show some of the materials that you have that you can learn to make use of this plugin a little bit better. We have completed our hands-on part. We did 2 exercises. First one was to downloading data, Sentinel-2 data from Earth Engine. The second one was building a workflow to compute land cover statistics from a land cover data that was hosted in the cloud. And we could get it into QGIS and use the model designer to build a workflow. If you want to learn more about Earth Engine, we have a lot of material on Earth Engine. This is a kind of good basic introduction that will allow you to start using the datasets from Earth Engine into QGIS. But if you want to do more, if you want to actually analyze the data in the cloud, use the full power of Earth Engine, we have a whole bunch of learning resources. If you just want a little more context on Earth Engine, you can start with this quick start workshop. Again, all the materials that we produce are open access and free to use. So you should be able to just watch the videos here, follow this. It's a short 5-hour workshop. This will give you a good working knowledge of Earth Engine so you can start analyzing the data. And for people who are doing research on remote sensing, it's worthwhile to learn Earth Engine in a more structured way where you can know how to do Earth Engine for machine learning and for doing change detection and so on. We have this course, End-to-End Google Earth Engine. It's a very popular course, which again, we have built it over multiple years and now it covers everything you need to know about Earth Engine. It's a 4-week course. Again, everything is available on YouTube if you want to do it as a self-study. We also link to some book chapters along with the videos that will help you learn specific topics if you're interested in. So again, you can work through these materials. And for people who have completed this workshop, I'll at least recommend this introductory workshop to get a little more understanding of how Earth Engine works. Even if you don't use Earth Engine directly, as you use this plugin, it'll give you more context around understanding the code. Sometimes you'll say, can't figure out what is a min-max value, but here's a code. Can I understand what the code is doing? And this workshop will help you towards that. The second one I want to point you to is the official QGIS documentation. This is available on the GitHub repository of the plugin. It has got sections on how to install. This is the one you used when you install the plugin. There are some tutorials here. These are the tutorials that I wrote for the plugin. The first 2 ones are the stuff that we covered in the workshop. So downloading images, building a workflow. This is a different example of doing something different, using some raster calculator to do some analysis. You can also do this if you want to, but I want to point you to the third tutorial. which is more from the perspective of Earth Engine programmers. And I want to use QGIS to create some visualization which are not possible in Earth Engine. For example, I want to create a globe visualization like this with data from Earth Engine. In Earth Engine, you can only create flat maps. It's only one projection. You can just create a flat map. What if I want to create a globe like this? But I don't want to download this global data set and do this in QGIS. Can I do this directly? So I want to show a workflow that this plugin enables, that once you learn Earth Engine and you want to create maps in different projections or pull data into QGIS for creating maps, you can use this. I'm going to quickly demonstrate the tutorial here so you can kind of understand how it works. So here we are in QGIS. What we want to do is we want to load some data. Now, one option is to use the plugin, but then the plugin is not very flexible. Earth Engine can do a lot of things. One of the things that the plugin will enable is now when I open the Python console in QGIS, my Python console understands Earth Engine API. That means here I can write Python code that is using the Earth Engine API and QGIS will understand. So if I say import E and I run this, this works. I have the Earth Engine API access within the QGIS environment. So I can write Earth Engine code like this. So I'm going to go and write some code. This is Earth Engine API code, which is loading this IPv6 climate projections data. This data set is widely used in climate research. There are different models and different scenarios, and you predict what will be the temperature and other climate parameters up to 100 years in the future. So we can write some code here. We are saying, I want to use this model under this scenario. What would be the temperature in the year 2030? So under this scenario, in this model, what is the predicted temperature in the future? You can see I'm writing some filters. This is the kind of code that the plugin uses under the hood once you configure it, but we are using those directly. And again, you have the full API access to Earth Engine. We can also apply some scaling. Again, when you load data from Earth Engine, you can't do any processing. You just can load the data. All of the other conversions, etc., you have to do it in QGIS. If you just say, I want to do this in Earth Engine, you can write some Earth Engine code. This is converting the value from Kelvin to Celsius. And now we have our average temperature in 2030. We can visualize this with this min-max parameters. And finally, we say, I have a layer which I've created in Earth Engine. I want to see it. I have this line called map.addLayer. If I ran this code in Earth Engine, this layer will appear in Earth Engine. But now, since we are running this using plugin, the plugin has this import called map. So I have this extra line which says from plugin import map. That means when I say map.addLayer, this map is my QGIS map. So when I run this code, the result of this will be loaded into QGIS directly. So you can see I have this new layer that was created, and I'll see the results shortly. This is using the same process that the plugin uses under the hood, but now I was able to create this layer programmatically and see this results in QGIS. And this is dynamic. That means I can change any of the code here, run it, and I'll be able to see the results here. So you can see this one is the temperature map of the world that we were able to create. And this is streaming from Earth Engine servers. The advantage of this is this layer is like a WMS layer loaded in QGIS. It will behave and it supports everything that QGIS can do. One of the things we can do is we can change the projection to be an orthographic projection, and that will display this data on a globe. There is a really nice plugin that I like to use, which allow you to create this orthographic projections very easily. That plugin is called Globe Builder. This is a plugin that's available in the plugin repository. The Globe Builder plugin is a really useful plugin. It works with any type of data. So if you just load a vector layer and you want to see this on a globe, just use the Globe Builder plugin and it'll turn this into a globe. I'll open the plugin and open the Globe Builder plugin. So the Globe Builder plugin has some options here. You can load some data, pre-configured data, but we already have a data. You can select the projection. This is which projection you want to choose. We say we want an orthographic projection. You can say, what is the center of a projection? Because the orthographic projection will display one hemisphere. So you can say, I want this coordinates to be centered here. I can also say, I'm interested in a particular region. I can say center of my current view, or you can specify a particular region. Let's leave this as the default one. And we have some other thing, the background. I just want the background to be white and some other options here. Once we configure, you can just say add globe to a map. What this does is you can see that my project CRS was changed to a new CRS. This is a custom CRS that's an orthographic projection centered on whatever projection I choose. And my map canvas is chained to that projection. And you can see QGIS is requesting Earth Engine to send data in that projection. And you can see my CMIP6 data rendered on a globe, which is being streamed from Earth Engine. Something that's impossible to do in Earth Engine. If you have to do this in QGIS, you have to download the data. But again, very large data set. You're able to use some of your Earth Engine API code to load this data and then render this on map with a globe. And you can now take it to a print layout and create this map on the globe. This full tutorial is available on the Earth Engine documentation. So go and check out the documentation page and you'll see the tutorials here.